is very flat.
What's up, everybody? I didn't realize that the, what are those called? Crickets was playing on there, too. Oops. We get Rumpus and Crickets to start off the show. A strange combination. It is Monday, March 22nd, 2021? Yeah, 2021. I'm Brandon, host of Brandon's Show. Hope everybody's doing good out there. Had a good weekend. Hopefully this week's shows are as eventful as last week's shows, which was an excellent week, in my opinion. Lots of good discussions. A few shit shows here and there, but that's to be expected, right? Let's see who we got into chat. Bill G. Sound is good. Thank you, Bill. Appreciate that as always. Ian Adams, YouTube. Danny Burgess, page 42. Arwin. I should make sure my microphone's working. Yeah, okay. I guess that's what Bill was telling me, huh? Ooh, wake up. RH. Anthony Burrows. Helen Degenerates. Zima Just Plaska. Earth is Flat. And Enigma. And Ian Adams, in case I didn't say him already, which I think I may have. How's everybody doing out there tonight? Good? Good. It's like 70 degrees here. So I am doing excellent. Spring is definitely in full effect, which is awesome. And I'm loving it because I hate the cold weather, personally. So any warmth. I'll take 100-degree heat over 40-degree heat any day of the week. But anyway, enough about that. We got a bunch of people in Discord already. I don't know what we're going to talk about today. I made some shit up for the show title just on a whim. So, actually, it was based on a conversation I had with, what's her face? Brenda. You guys remember Brenda, some of you. I had a mini debate with her yesterday on her channel. Her new channel is like Ellen of Cyrene. And falsification came up, and there was an interesting exchange about how we could optically falsify the globe model. And that's something we talk about here all the time. So, yeah, threw that in there. Figured we might discuss it. If anybody listened to that debate, which is doubtful, I think it only had like 40 or 50 views. We can talk about that. I think Travis has got some stuff if he's in tonight. I know he was resting. He was out taking observations, etc. So we'll see what he comes up with. And who knows what else will happen. I'm sure we'll talk about gravity a little bit. That seems to be the hot topic for sure. Heard about it all weekend all over the place. So we'll see what happens there. If you want to support the show monetarily, you can do so through Streamlabs. There's the link, and it's always pinned at the top of the chats and in the video description. That cuts Google out of the middle, so that is awesome. Or a super chat, and I will read your comments either way. If you want to join the show, you can come into Discord in my Brandon's Flat Earth, what is it called? Brandon's Flat Earth server. That's right. Brandon's Flat Earth server. Come on in and join in the show, or just come in and listen. We got people that do both. Or if you want to play with the trolls, they're there 24/7 for your pleasure. Something. But if you're into that kind of thing, come on in. All right. Well, without further ado, let's go into Discord and get this show going.
Well, maybe we can figure out what Bob did and what kind of gyro we used. They told me over in Gems you can make a one-dimensional gyro for as cheap as like a couple $100. So I mean, you know how to build it. You know how to build a gyro? What?
An optical one?
Yeah.
Okay. Yeah, do that. Then you can just like twist it around 90 degrees and there. That'd be fantastic.
We'll have to figure something out.
Yeah.
What's up, guys?
I
We're
need
live.
to get it.
Hey, Brandon.
How's it going?
Lovely.
Good.
Good. Got quite a few people in here to start off the show. Good to see a nice crowd in here. We got Aaron A. What's up, Aaron? I think that's Aaron Armstrong. He might be on the road or working. Ellie B.
Yeah.
How you doing, Brandon?
Good, Ellie. How are you?
I'm fine. I was just a quick one. Oh no, I'll leave it. Yeah, I'm fine now.
Okay. All right.
Yeah.
Good. Brian Leakey. What's up, Brian?
Hey, what's going on, man? I got a simple little experiment to run by y'all to get to the bottom of one of our situations after you introduce everybody.
Perfect. We'll come
I
to you
can't
first.
wait.
Yeah.
I can't wait.
And car in Kentucky.
Ooh, that was better.
Was it close?
It was better. Definitely better than the last time.
All right, we'll get there. F Evangelist.
Hey, Brandon, how are you?
Good. How are you doing?
Good, man. I'm on the road working. I'm not sure whether Aaron... Oh, Aaron's gone. He must be working hard. Anyway,
Oh, okay.
I'll probably be quiet because I have a lot of background noise.
Cool. No problem. And Mark. What's up, Mark? Helvetica
I'm good. Good to be here, everybody.
Good. Jimbo. What's up, Jimbo? No? Ruhif. How you doing, Ruhif?
Same as F Evangelist. I'm not really here.
Okay.
I'll probably go on
all
mute
right.
in a minute.
All
But
right.
good morning, everyone. Good morning.
Good evening. Jeremy.
Unlike these other guys, I am really here.
All
Hello.
right. Fucking A. It's awesome. Bob Dole.
Hello.
What's up, Bob? How you doing?
Oh, I think I'm doing all right.
Yeah. Okay. Good. Then we had one more person pop in. We'll say hello to before we go to Brian Leakey. Arwin. What's up,
Arwin? Yay!
Oh,
Yay.
Arwin.
I found it.
Arwin? Welcome to the show, man. I don't think we've had you on here before.
No, that's correct.
Okay. Great. Good to have you.
Do you still have your show on?
Oh, yeah.
Very good.
Okay.
Cool. All right, Brian, let's hear it. What's the idea?
All
man?
right, yeah. Shout out to Arwin, man. Whoever's not subscribed, it's ARI. What is it? Double JN Arwin. He's always got some good stuff going on though, man. Look it up. But okay, so unfortunately, Jeremy, this doesn't have to do with the straight line test, but it's just as interesting. But it's something I think we can. If somebody has a vacuum chamber, we can get to it. I made a little video, but I'm just gonna describe it simply. Okay, because we've been having this argument about how gravity affects gas, and it always seems to boil down to the gas in the vacuum chamber. Okay, and for who hasn't seen it, we see the helium balloons. It boils down to a helium balloon in a vacuum, and they say it drops in the vacuum chamber. We say that follows the relative density disequilibrium rules perfectly because the helium is not going down. The balloon's pulling it down because a void would be less dense than the helium. So there's nothing to support the helium, but the helium in the balloon is still blowing in all directions, obeying gas laws. Now, the counter to that is that, and I've heard this from Bob, I've heard it from Rumpus, I've heard it from other people, that, and they could be right, but I got a test to figure it out. They say that the gas, when you first put it in there, because one other thing, we've all seen the bromine in the evacuated tank next to it. And there's a valve in between, and the professor lifts the valve, and he explains the gas law, how there's no change in energy, there's no gain in temperature, no gain in pressure or loss in the system. It's just a change in entropy. So having said that, what we do, they say that the energy runs out when we first put the helium in the vacuum chamber, just a little bit, let's say, that it's bouncing around and it's following gas law, blowing in all directions. But they say, like anything else, it will run out of energy and stop moving. And I and most of us disagree with that. Now, I thought of a way to prove that. They won't tell us how long it takes. I've even asked for would it take minutes, days, years? How long would it take? And I've never got a straight answer. But so how we do this is we get a bell jar, okay, and hopefully somebody will beat me to this, but we get a bell jar and we get an alarm, and we can always, anybody can demonstrate with a decimal meter that things are louder, okay, with the medium, and as the air is evacuated, the sound decibels start dropping because it needs a medium to permeate through. The sound does. So we get an alarm and put one at the top, and we put one at the bottom. Okay, and we add just enough helium to make, to where when we first put a little helium in the void, in the bell jar, we get a little bit of noise, just a little bit, and measurable by the decibel meter, and then we'd give it time and see if the alarm at the top is producing less decibels because the air is dropping to the bottom. So the point is the air at the bottom, the alarm at the bottom should be louder and produce more decibels over time if the air is running out of energy dropping to the bottom in the bell jar. You get me? Y'all
Yeah,
get it?
is that's a
measure
very
this?
interesting idea,
That's
Brian.
gonna
Is
prove a
that
gradient,
is that a fact that the sound should increase, the decibel level should increase or decrease depending on the amount of gas that the alarm is surrounded by? Do we know that?
Yeah,
for
you
sure?
can
Why don't we
demonstrate.
just-
You can
hold on a
demonstrate the
second, Brian.
decibels dropping. Yeah, one thing you could demonstrate the decibels dropping as the air is evacuated down to 0. So, yeah, go ahead, Jeremy.
Okay.
Why not just
Wouldn't it be
measure the
easier-
pressure at the top and the bottom?
Are
Yeah.
you
Wouldn't it be
Jeremy
easier to
Rohif? What
just-
the fuck, man?
Well, I
Go
was going to
ahead.
say
Huh?
the same exact thing. Why don't we just measure it with like a pressure gauge or something? Or it seems like a very complicated way to measure the pressure.
Well, why did you choose? Why are you going in this direction instead of some kind of
Because
pressure gauge?
well, the pressure doesn't. I guess we could do it with pressure, but the decibels would be absolute. In other words, you could say margin of error with the pressure gauges or whatever. Maybe one's not sensitive enough or something. But the point is when you evacuate all the air out the jar, there is no decibels, 0 decibels. Okay, so if you have just a tiny bit of air in there, then you have like just 1 decibel, or 0.5 decibels. So if we have an alarm at the top and the bottom at first, making the same decibels, okay, then if we kept evacuating it, then we'd get no reading on the decimal scale, okay? But if the air has any change at all, there should be a difference in the decibels if it drops to the bottom. To me, it would just be very conclusive. I don't know. We could do the pressure, but I'm with you on the pressure reading. But
I would do
just
both,
another
maybe.
example. That's it.
Conclusive to what end? To prove that a gradient will form after the gas has expanded within the container? Sure.
Proving that gas doesn't go down, go boom boom, right?
I fucking.
Well, how doesn't it prove it? I don't know. It doesn't prove or disprove it. It would just prove that there would be gradient forming. No?
I don't think there would be in a vacuum. I think air expands in all directions, especially in a vacuum. And unless you want to, and if you want to introduce a void of outer space where there's no temperature, if you want to introduce a Fantasyland spot, not you, Arwen, not you, but if somebody wants to introduce La La Land, they're going to say that the sun, the room temperature keeps heating it up, keeping it expanding. But in real life, yeah, you're right, Arwen. And in reality, it's expanding in all directions, especially in a vacuum, right?
I've
Well,
been
we're talking
challenging
about a vacuum chamber, right? You were talking tests in physical world, right? Not
Yeah,
three-dimensional outer space. So I was just pointing
Exactly.
out, like, yeah, gradients could form. I'm all for that. I think that gradients naturally form once the gas settles within the confines of the container as a secondary effect.
I disagree. I don't think there'll be a gradient in if you evacuate all there and get the best vacuum you can in a bell jar and you add a little bit of helium. I think you'll maintain that pressure until entropy takes place, until it seeps out. I don't think it'll ever accumulate at the bottom.
Okay, so you think that with the setup, the alarm sound coming through will basically stay equal, bottom and top, throughout the
Right.
experiment.
Yeah.
All right.
And to make it more realistic, we could do it. Do it in a pipe that's like 10 foot tall, because the only reason in nature we get a gradient is because of temperature. That's the only reason we get a gradient. In other words, the gas is created here at the ground, and just like air conditioners and refrigerators work, the gas expanding up higher, the gas goes past Mount Everest, it keeps on going up, and as the gas expands, it cools down, it gets super, super cold, but there's got to be a barrier up there or it would keep expanding, period.
This is actually something I've been challenging the Globers for a long time with. They claim that if you put all helium inside a tank, that eventually it will settle and there'll be more gas on the bottom. And I was like, well, I'm not so sure. Why don't you show me? And they can't show me this. So
I really like this idea. I think this would be a pretty simple experiment to do, and the results would be very interesting either way. Yeah, it could turn out that there's a gradient, that forms, or it could turn out that the gas all falls down, or that there's no gradient at all. I think you'd be able to decipher the results either way.
But if you follow gas law, go ahead, Jeremy.
The gas is never going to fall down to the point where you could sweep it up. That doesn't happen.
Yeah, I know, but that's
if there's
this
no
experiment
change in temperature,
is that would be one of the possible outcomes theoretically of this experiment, right? That the gas falls down eventually.
According to gas law, if the temperature stays the same, if the temperature around it stays the same, then according to gas law, the gas will expand. It will keep expanding. Now, if you heat up the gas or cool it down, you could start getting gradients. But under constant temperature, it's never going to settle at the bottom. In my opinion,
the amount of gradient you'd be measuring in this would be so tiny. You'd have to make sure the top of the tank stayed the exact same temperature as the bottom of the tank. So this is harder than it sounds.
Yeah.
That's why I said I don't want to get too out of hand with the size of the pipe. We could do it vertically, just on the ground, 20 foot wide or maybe 20 foot tall. There's no change in temperature. If as long as a void or a near absolute zero temperature is not induced, then reality is going to take effect, and the pressure is going to keep blowing equally in all directions.
How long are you going to give it to settle, Brian?
Rapid expansion.
How long are you going to observe it for?
That's why I wanted an approximation for it, but nobody will say how long that takes. Nobody will even touch it. They won't even tell me if it's years, minutes, hours, days.
Because effectively these little gas molecule bouncy balls, you got to wait for them to stop losing their bounciness and just come to rest effectively on the bottom of the container. That could take 20 years or 10 seconds. But who knows?
When gas expands, it cools. That's the way it is. The rapid expansion of a gas causes cooling. It's not going to change.
That's my whole point. That's my whole point, man.
So, Ruhif, you're under the impression... My bad, Jimbo. Go ahead.
Cooling systems work on the differential of pressure. They take
That's my entire point. But in the system though, the gas escaping the gas filling the vacuum or filling the void, there's no change in temperature. You can't get an AC by filling a vacuum. You got to expand the gas, and you got to expand this. You got to expand the system.
Ruhif, let me ask Ruhif a question real quick. Ruhif, are you under the impression that eventually these gas molecules will lose all their energy and they'll just fall to the bottom to be swept up?
Oh, he did say he was working. He might not be able to answer, but same question to anybody on the panel. Does anybody believe that the results of that experiment would be that the gas would eventually pool towards the bottom and there wouldn't be any on the top?
The ballers have to hold this. Every debate about it boils down to that.
Yeah, but does anybody on the panel believe that that's what's going to happen?
If anyone is claiming that the gas molecules are losing energy, it must be a matter of time before they lose all their energy.
Who even says
a little bit of energy?
Who even says that this happens? Who's making this claim?
Bob just said it. Bob Nodell agreed with McToon. No, McToon said it. Rumpus said it. Bob Nodell said it. Who else said it? I don't want to.
I had Kosho in the after show saying the same shit. Not that it would fall and be swept up, but that they would lose energy. He doesn't understand elastic collisions.
The point is filling a void back up, filling a vacuum chamber back up, does not cause a change in temperature or pressure in the system. It only changes entropy. So you're not going to gain or lose energy. So you can't gain or lose temperature. You're just the air just goes back into the void, into the vacuum we create. To me, it's self-explained.
The in the after show that Jeremy's talking about, because I was listening in and I think I might have spoke up several times, but the way he said it was that those molecules that are bouncing around, the gas molecules that are bouncing around, they won't lose their energy. He claims that what they'll do is they will bounce into the side of the container and transfer the energy, but all of the energy still remains in there. It's just whether or not it's on the walls or in a molecule.
Huh?
I don't know if that affects what you're saying.
No.
That's what they'll try to pull on
but
you.
during the
They'll say
regular
that-
show,
something like that.
They'll say it
during the
doesn't
regular
lose
show,
energy, it just transfers it. Apparently.
sorry.
Well, that's weird.
During the regular show, though, he said that at first it goes rushing in, so it's full of energy. That's the way he put it. And he said, it bouncing around. I don't want to misquote him, but I do remember that part of it. As he said, at first it rushes in and it's bouncing around, full of energy. So
They might not
Jeremy,
even have
ping
their
him, see if
stories
he's
straight with
available.
each other.
See if Kosho's around.
All right.
he could be right, but to me this should be demonstratable. If my common sense says otherwise. It says that it's going to blow out in equal directions. The balloon's always going to inflate equally on all sides in a near void. But I could be wrong, But I want to. It's demonstratable, and that would be a good way to maybe do it.
So you would have to obviously control for temperature around the chamber, right?
Yeah. That's why I suggested doing it just on the ground. 20 feet. It would take because then you couldn't say up or down if the temperature stayed the same. No, you couldn't do it on the ground if it's a pipe. You don't want to go too high with the pipe though. But Jeremy, you remember him?
Right.
You had me ask him, or you started to say, but I beat you to it. I think to ask him how long would it take for them to run out of energy and go down to the bottom.
Yeah, I mean, if anyone's claiming that their gas molecules are running out of energy, how long before they stop and you can just sweep them up? It must be a matter of time. I think that's what Ruhif was alluding to just now. But as far as
I think Bob meant it run out of energy and changes states. Maybe I don't know.
No, he did say
They're
something
not
about it
gonna
changing
run
to a
out of
liquid.
energy, but that doesn't mean that a gradient can't form. I wanted to ask about the setup that was proposed earlier in the vacuum chamber, releasing some helium in it. So what if there is just this minute pressure differential, this minute sound differential? It's so small, but it is there. You can't deny it every time, whatever you try. But it's just really, really small. So would you then still say, okay, a gradient doesn't form? And by the way, this would not support in any way that gas goes down, goes boom, boom, right? It's still
it could disprove it
within the container, and then whatever happens secondarily.
Yeah, we'd set up some controls, right? But to me, it could disprove it.
No, I think that's a good
This would be
question. No, I think you're misunderstanding the question. If I understand it correctly, you're saying what's the baseline?
It would be controls. The baseline would be, evacuating the air. Evacuating the air until we just barely got any noise at all, because you can demonstrate as the air is being evacuated, you see the decibels go down and it gets louder. I mean, it's starting to get less loud. It's demonstratable. So we wait till there's just a tiny bit of noise detected, and we check the alarm at the top and the bottom. Get over time, there should be a change in decibels from the top to the bottom, in my opinion.
This would be so hard to do because you're trying to measure this extremely minute pressure differential. So you're going to need to keep the temperature exactly the same on the top and bottom of this tank, or it ain't going to, your controls are fucked up.
Yeah, but air going back into a vacuum tank does not make it hot or cold, man. That's it just is a change in entropy is all. Now, if you blow air expanding into out into the open, it cools down and shit, but in the system that's been evacuated, it's just a change in entropy, not in energy, meaning temperature, pressure, I
think Jeremy might be right. What if the change in the decibel level is so minute? Because we're talking about if there is a gradient in there, even it'll be just so minimal, of a difference from the top of that chamber to the bottom of the chamber. Would you even be able to measure it?
And if you have a tiny temperature difference in the top of the chamber to the bottom of the chamber, that could, obviously affect the results.
Well, I was just going to say that could be a very interesting follow-up test where there's cooling and heating elements at sides, and then see how that affects any potential pressure differential.
Yeah.
Great point. See, he's thinking with me.
Are we talking of a specific gas?
Helium.
Well,
I actually
could
use
be any
the temperature.
gas. Could be
Yeah, but
air,
it could be any gas,
helium.
right? It could be any gas.
Well,
Right,
we
you
all
could test
know.
it. Maybe there's even differences with different type of gases. You
Well,
don't
we all know
until you test it.
propane and butane are heavier than air, don't we? Because you can pull it in your hand.
That's why I suggest using helium, but damn, I forgot what I was going to say. Never mind.
Helium, if you put helium into a balloon, like a party balloon, and then put that balloon inside, let's say, a weather balloon, and filled the weather balloon with hydrogen, the helium would go down.
Yeah. Oh, I remember. I was actually going to say I used the temperature differential to explain the pressure gradient on Earth. You know, it's cold up top.
Yeah, it's obvious.
If
you let gas into a vacuum chamber, surely
and then falls, and you have a cycle going on there.
Well, it's got to stop somewhere there, Jeremy. The air is a byproduct and a partial cause, but the air would keep expanding if there wasn't something to stop it. Period. It would keep expanding if there wasn't a gradient to begin with. But the air, the cool temperatures does help maintain that gradient, but it's pretty eventual. But there's got to be something stopping it, or it would keep expanding.
Surely, if you release gas into a vacuum chamber, it's no longer a vacuum chamber; it's a chamber of gas.
Right. We're talking about just the best vacuum we could get, and just because you can demonstrate that sound going away, and just in a bell jar.
What about here's another concept. What if you just released a coloured gas into the vacuum chamber, and then you'll be able to see whether that coloured gas pulls at the bottom, because it'll be blue or pink or yellow or green. And
you could use bromine or yeah. I'd like to use a gas that's lighter than. I'd like to use a light gas for this, rather than something heavy. But I mean, whatever.
Well, the problem is it's only light and goes up because it's in air. Once you remove that air, it will be the heaviest substance in there, so it will go down.
You make another valid point. If relative density holds true,
it's nonsensical.
If relative density holds true, it'd have more density than the
no air that's in there, so it would go down.
Yeah.
So
with Arwin's here, he knows about relative density. Would say that there should be a gradient in that vacuum. No, Arwin.
If you've sucked all the air out and you add gas, it's only got itself in there.
So it sounds like you guys are now agreeing with Bob, though, Brian and Jeremy, that it would eventually settle to the bottom because it's the heaviest thing in the chamber.
It's not that it's settling to the bottom, mate. It's just that there's nothing heavier than it in there.
I mean, I think gas law dictates.
This is where we get confused.
Well, tell us what the confusion is, because I'm not getting it so far.
We are in a density tower here, and you can tell that by just looking at the bottom of clouds. Why are the clouds up there? Because they're less dense than down here where we are.
Yeah.
And we've got clouds that are double that height, which obviously are less dense than the clouds we see lower.
The thing is, Brandon. Sorry, Brian. The thing is, Brandon, Bob's saying it's because of electromagnetic static ether or some shit. And I'm saying, no. We have the cause for it. It's relative density. I think that's the only difference.
Well, okay, so let's say you do the experiment and you get it to all pool at the bottom. Now, what have you done as far as answering that question? Is it because of density? Or is it because of electrostatic?
They'll say you proved gravity.
No, you have just proved that there's only that gas in there. It's only lighter because there's a heavier, denser material like air in there. If there's no air, it won't go up. Never so easy.
Is that even true? It won't go up. My understanding was that the gas just bounced around constantly. But you think it'll pool at the bottom?
I think it is only light because it's in a denser medium. Now, you can take any gas. Now, I know because I used to run LPG vans, and when I had my tank fitted, I had to have a runoff area and no walls around the tank because LPG is heavier than air. So it had to be able to flow. Now, I know that's heavier. But if you put that LPG underwater and released it, it would go up because water is more dense than LPG. And that's exactly what we live in. It's so simple when it clicks with you.
I mean, Chem for Kids is saying that, here, let me read this off real quick. Gases can fill a container of any size or shape. It doesn't matter how big the container is, the molecules spread out to fill the whole space equally.
When you buy, listen to this. If you buy a new bottle of, let's say, Calagas for your cooker and open it, you will get air out. For the first minute or so, you will get compressed air out because the LPG that's in that Calagas bottle is heavier than the air. So the air sits on top of it. So when you first turn your bottle on, you'll literally get a spew of air out of it because they do not vacuum the air out. They just pressurize the gas in. So you've still got that lump of air in there.
Yeah, that's a little different with the pressure. But what we're talking about is, I think Jeremy's right. If the temperature remains constant, then it'll follow gas law. It's all dependent on the temperature. They go hand in hand.
You'd also want to purge the container probably a few times to make sure there, in fact, is only helium in it or whatever you're going to use because of what Brian just said about, when they fill it, there's air in it. So you're going to want to make sure that there's no air in it. That's what I'm saying. This sounds easier than it is.
Yes, it is. And I know that because I took a fucking bottle back that wouldn't light the fire. And the bloke said, it's a brand new bottle, mate. It'll have air in it for the first few minutes. And lo and behold, just open the tap and the air spewed out and then you started getting gas. Once it's purged that gas out and it's refilled with gas, obviously there's no air in it. But a brand new bottle has air in it. And it sits on the top. And that's what you're doing with the vacuum. You're removing the air, which is heavier or lighter than what you're putting in, and the gas, instead of going up, will be the heaviest stuff in there.
Hold on, here's Ruhip.
It's only relevant to what it's in.
In a gas tank, gas is in a liquid state. It's pressurized to a liquid.
Not all of it, Arwin. Not all of it. They can't.
Usually that is what it is. And hey, in a liquid state, who knows?
They can only fill them 80%. They have to leave 20% for expansion.
All right.
Let me ask Ruhip.
So your car tire, it sits for a week. Is all the gas at the bottom of the tire? When you put helium in a vacuum, it's no longer
bromine in the experiment. Just use bromine. Don't worry about decibels.
Two different gases.
Color's all you need.
If you have filled it up with two different gases, one being air, one being helium, you would get a separation, I would imagine.
Hey, I think that was a pretty good point, James. James, that was a pretty good point. But
no.
Sorry.
It's a bit like tractor
why this is feasible, guys.
Hold
in
on,
a
guys.
tractor tire, they half fill it with water.
All right, hold
and
on.
it gives it suspension.
Jeremy, you were going to ask Ruhif a question.
Yeah, Ruhif, you here?
I don't think he is.
Yeah.
Oh, I thought I heard him talk.
He's gone, isn't he?
Okay.
I thought I heard him say something. Anyway,
I got a question if you guys don't mind.
Arwin, hold on a second, though. Arwin, you wouldn't be opposed to relative density causing a gradient in the container, would you? Arwin? Did I disconnect?
Oh, sorry. You asking me something?
Yeah. You wouldn't be opposed to relative density causing a gradient in this container that we're proposing?
No. What?
Because it's heavier than.
I don't know whether I think that really whatever gradient we're going to be dealing with, it usually has to do with just other influences potentially, and just the sheer size of this realm's container, and we don't know all elements about it. So, yeah, dynamic system. But
yeah, it's dynamic.
Who knows how much the size actually has an influence on gradient formation, or if temperature differential has more impact on gradient formation.
Allow me to say real quick, the reason I think this test is feasible, guys, is because we can evacuate the bell jar until there's just a tiny bit of noise, like just a just a 1 decimal of a decibel. You know what I'm saying? And that being the case, if we first let that in there and this gas has got full energy as it's being evacuated, okay, and we got it dropped down to 1 decibel, it can't remain constant if the air is dropping to the bottom, whatever gas it may be. If it's dropping to the bottom and we just barely got a barely reading and we barely heard it, it can't remain constant if the gas is pulling at the bottom.
What about Effie Evangelist's idea of just using colored gas?
Yeah, they're just overcomplicating it, Brandon. Just use bloody bromine, and then you can see it'll separate her at what? Like the brown will be at the bottom, and it'll be clear at the top, or you'll see a gradiated color scale, or I don't know. It's just so simple. I don't know why we're making it so difficult.
Here's where I need help, guys.
This
is where I need help on this.
As long as they have an excuse, we got to think of something, right? Go ahead, Neil. Or go ahead, Benzo.
James, I just need help because everybody's saying what gas to do in a vacuum, but once you put gas in a vacuum, it's no longer a vacuum. So I need help on that.
The point, James, if you evacuate it and then you just put a single gas in, then you're not getting radiation through, part of it's helium, part of it's oxygen, part of it's nitrogen. You're just putting a single gas into a, for want of a better term, a void. So that way it's only bromine in there, for example. So either the bromine will fill the entire space and just swirl around and bounce around forever, or the molecules will lose their momentum over time and they'll settle to the bottom. That's what we're trying to figure out.
Our whole point is that in our reality there is no void. There's just temperature changes which affect the pressure changes. In our reality, in their reality, everything starts at absolute zero, which they can't reach, at a absolute zero pressure, which they can't reach. To us, anything that's going on around us, if you start evacuating the air, it's going negative. There's negatives, but you can't do that with math. It's too complicated. So they have to make everything positive to make it feasible with the mass. Even with the Coulomb's law, they found a way to pretty much make the electrons where it's all pretty much positive to make it measurable.
What?
But they say they can't make a perfect vacuum. So isn't there already a little gas in it?
Yeah, let me simplify that by saying, Arwen, everything works on equilibrium. Like the density to equilibrium is a better way to put that.
Billiards?
Thanks. I didn't know that. No, that's okay.
Yeah, right. Yeah, he's one of the creators of the concept.
You hang around here, Owen. You'll learn some things, buddy. Don't worry.
Hey, good to know what got out there.
A somewhat easier experiment would be to just develop a very tall chamber, airtight seal, and you have an adapter on top, you have an adapter on bottom, and you can specify a particular pressure, and you can see how long it takes, whether you evacuate it from the top or you evacuate it from the bottom. And if it holds true that gas tends to pool at the bottom or has a bias bottom, it would be easier to get to that pressure by pulling from the bottom.
If it's the only substance in there, it will be the heaviest substance, won't it?
But again, if it holds true that it's what you're claiming with gas going in all directions equally, then when you evacuate it from the top or the bottom, it should take the same amount of time or the same amount of power. But if it has a downward bias, then it's going to be easier to take out the gas from the bottom and get to that pressure that you specified sooner.
Biodual Chemistry for Kids is claiming that gas fills the container evenly.
Okay, that's awesome. But do you have a problem with what I proposed?
I know, but you said we were claiming it. It's chemistry that they're teaching children. Is claiming
that's fantastic,
that, so.
Jeremy. Do you have a problem with the experiment that I proposed?
Do you have a problem with
and gas law?
Do you have a problem with them teaching children that gas?
We can get into an argument that's not productive. That's fine. But what I proposed, do you have a problem with that? Because I feel like that would be better, and you don't have to do any coloration. You don't have to care about what gas is inside. So long as it's a gas, you're pulling from two different locations, the top or the bottom, and you can specify a pressure. One of them will take longer than the other, or they'll take the same amount of time, and that'll confirm many things.
What is the expected differential biodual that you're talking about with your experimental setup? Are we talking there might be a split-second difference, a second difference, a minute difference?
Oh yeah, I'm not making any predictions as far as like the actual timing. It would all depend on how tall your container is. If it's a short container that's a short height, it's not going to be a big difference. But if you have let's just say 20 feet, you have a 20-foot tall column, you should be able to see a noticeable difference.
A noticeable difference. Yeah. What's wrong with just using the colored gas and looking at it? What's the problem with that idea? Or do you think that would work?
Yeah, I don't know. Let's just make it as ambiguous and complicated as we can. So that way, whatever result we get, we can fucking argue about it for the next 6 months as inconclusive.
Right. But
just use color. It's just simple.
I want to hear his answer, though. Biodual, do you think that would work? Or do you think that there's a problem with just using colored gas?
Can anybody give me a link or a friend invite over to Pseudoscience vs. Science? I deleted my account. I lost everything, man. So
we're in the middle of the show.
I don't inherently see a problem. I think the biggest problem would just be time, because when you introduce, so let's say you do get it down to a vacuum, to the vacuum you want, and then you introduce, let's say, a colored helium or a colored whatever gas you want. You introduce that specific gas. When you put it into that container, you're introducing a velocity to it, and it's going to take a long time for that energy to dissipate. And then you're also going to have to fill that container with enough of the matter so that you do fill the container with that color. I think the biggest problem is just time rather than actually doing it.
So why can't we just shake it up? Put the gas in there, shake the fucking thing up so it fills it up.
Hold on. That's true. Is the container still going to be in a negative pressure system?
No, it'll always be positive.
So it'll be positive. So it won't be a vacuum then at all.
Right, when you introduce something.
Negative
so you can bring it to
what's negative pressure? Jeez.
If it's in a negative state and you open it, it's going to draw more air.
What are you talking about? Negative pressure doesn't. That's not even a real thing.
No,
there is pressure, Brian.
Hold on, there is a term for negative pressure, but it's a certain situation. It's not a measurement of pressure. It's a situation.
It's a medical term they use in hospitals for people that have airborne illnesses. They push them in a negative pressure.
So when let me ask you this then.
Possibly make
you guys heard of Mythbusters? Mythbusters did an episode with a train car, one of the oil ones. They're kind of round cylinders, black. And they turned it in, they sucked all the air out like a vacuum. And it just got to a point where the entire thing instantly crushed. It bounced off the railroad platform it was on.
Right.
Would that be negative pressure?
No, the structural integrity of the material that was surrounding that vacuous space was being pushed on so heavily by the atmosphere that it couldn't take it. So then it collapsed in on itself.
No, that would be kind of a negative pressure system. Yeah.
From the inside, it would be
relatively. Yeah, you're sucking the air out. It's putting pressure inwards on the container. But to get back to forget about negative pressure, because we're just confusing ourselves. There's not a measurement of negative pressure.
Right, but to get back to what you were saying, Brian, yes, you could bring it to a vacuous pressure, but as soon as you introduce that specific gas that you want, then it will be less and less vacuous. Yeah.
I was thinking the only way you could probably make that work is have one container inside another one and make sure they equalize. But I don't know how you do it. I think it would be physically impossible. Because if you
have a container and you put gas in it and it equalizes. To me, this is absurd, gentlemen. And I don't mean any disrespect, but your car tire, all the air pressure in it doesn't settle at the bottom. It's not exerting more pressure after a week of sitting at the bottom of the tire.
No, it
inside the tire, all that pressure is exerted evenly. I mean, if it didn't, then it'd be like a bucket of water. When you twirl it around, the water stays in it. If you took off really fast, your tire would be unbalanced.
Yeah, they're saying it's just so slight. It's like everything else with this globe shit. They're saying it's just so slight you wouldn't notice. It's nominal, negligible.
Yeah, but where you take off fast and it's unbalanced, it would stay unbalanced.
Yeah, but it's just
because you're keeping it in that position like the bucket of water.
It's just a negligible
don't
amount.
Start me on about Don't start me on about tyre pressures. I don't know how 30 psi can hold up 350 pound on each corner of a car.
Well, you got the strength of those tires, and they're very strong.
Well, you let the air out, they will collapse.
Yeah, but when you pressurize the tire, you're also getting the strength of the tire.
Yeah, but
it's
it
not
doesn't
so strong
increase
without the pressure.
You can blow a tire up off the car, put it on the car, put the weight on it, and it still stays exactly the same PSI. It is. I can't.
You also. I understand what you're saying, but you're also strengthening the walls of the tire too.
Because the tire is a closed system; it doesn't let the air out. So why would it change?
Yeah, but you'd have thought it would have increased the pressure, wouldn't you? With 350 psi, 350 pound on it. I mean, when we corner weight a car, the fronts are over 350 pound, and yet there's only 28 to 32 psi in the tires.
Oh, I see what you're saying, Brian. The air on the inside gets displaced by that weight, so it moves around. So you have, with the full weight of the car on a tire, you'll have more particles above that axle than below, yet you have the same PSI.
Yeah.
It's just gas displacement at that point.
Okay. So you're saying, Biodual, you're saying there is a gas pressure gradient inside your tire, but it's reversed.
No. If you just have a tire and it's pressurized, you'll have an extremely small gradient. I don't know how specific or I don't know what unit of measurement that you can do to determine it. But when you put the weight of the car on, you do see that the middle is now lower than it was without the weight, yet you still have the same PSI. And it's just because the weight pushes down, so the air that's below the axle now gets displaced above the axle because of that weight distribution.
Let me ask you the same question I was going to ask Ruhiv. If you put gas in a container and you just wait long enough, will the gas eventually run out of energy?
No, because if it runs out of energy, then you're talking about a 0 Kelvin. So no.
So the gas isn't losing energy over time.
See, I don't know about that, because I was working on Friday when you and Kosho were talking about that, and I'm not knowledgeable enough about elastic collisions, and then when it gets down to, I don't want to say quantum level because I don't think it is, but when you get down to that molecular level with energy transfer and energy usage, I don't know enough. So I can't really say without it being 100% opinion.
I mean, wouldn't we have found some gas molecules like laying on the ground?
Yeah, I have.
No, like I said, because that would be a 0 Kelvin situation.
Only in 0
What
Kelvin.
would your opinion be?
My opinion is that they lose energy and they gain energy within a system. So when they bounce, just like a bouncy ball will lose energy in its height as it bounces, if you introduce energy into that bouncy ball, you can keep it a steady energy even though it's losing and gaining at the same time. So I think that's what's happening, but again, it's just 100% opinion.
So let me give you an example, because I want to clarify this a little bit. So you say 70 degrees. I've got a vacuum chamber in this perfect 70-degree room, and I fill it up with gas, we'll just say fucking helium, okay? You're saying that after a while, those molecules that are bouncing around in there will do what? Fall down to the bottom of the container or continue to bounce?
Oh, I would say continue, because you'd be maintaining a 70-degree temperature. But if you're not maintaining 70 degrees, but you are at 70 when you start, and there's no way to maintain that temperature, I think the room temperature would decrease over time because you're not adding any energy to that system.
Think about that.
No, this is a room that always stays 70 degrees. So as long as I keep that room at 70 degrees, you think the gas will bounce around and maintain the same activity?
Right. Yeah, I agree. I agree
about
because
this, y'all.
you're maintaining the energy essentially.
Yeah, think about this real quick. If it would be easy to make an air conditioner if all we have to do is create a vacuum and then add some air into the vacuum, and it would start losing energy. Then it would have to cool down. It would have to pull heat from the room. So we could cool rooms essentially with that concept, and that's not how it works, right?
It might work in that way, but that is such a small scale that it wouldn't be efficient or we wouldn't notice it for the duration of time that we're trying to use that tool.
So
there's no change in
let's
energy,
just say you
only
had-
entropy.
Let's just say you had different temperatures rather than just 70. So if it's the temperature, wouldn't the gas molecules slow down or accelerate depending on that?
Oh yeah,
That's
of course.
the whole point. Look, that's the whole point. Is if it were expanding into a vacuum, if the air from the ground was expanded into a vacuum, it would be no change in energy, only entropy. But it gets cold as shit up there because there is a container. There's a wall to hit. So when it's
What
expanding,
I'm saying is the gas molecules that slow down because of a temperature change, they're slowing down because of that and not because of gravity.
They go hand
it would
in
be
hand.
a number of things. It would be a number of things. But I think what you're trying to say is, let's say the room temperature is 70 degrees, but the container and the gas that's inside that container is at 60. Is that kind of what you're saying? You have a varying temperature within this entire
Well, I'm
system?
saying if the temperature is what dictates what excites the gas molecules, right? Then
that'll be part of it, yeah.
Whatever one it is, higher temperature they slow down or speed up. Whatever one gets them to slow down.
They go hand in hand, but I don't think y'all understand what I'm saying, man. What I'm saying is, if you listen to the professor, he says if there's already a vacuum there, okay, in the system, okay, and we introduce the gas in the system to it, there's no change in energy. There's no change. That means there's no change in temperature and pressure. In other words, if there's a vacuum above us, okay, and the gas was expanding up there like it is, everybody can agree to that. It wouldn't get colder up there, okay. But
Brian, I'm only asking that because every day we have a change of temperature. So that's
right,
why
it's a dynamic system. Yeah, I understand. It's a dynamic system, but it's obvious on how cold it is. It gets almost to absolute zero up there, about 70, 72 miles, that it's not expanding into a vacuum. It wouldn't be there would be no change in energy, so no change in temperature. So we can demonstrate this shit on the ground, man. You know.
No, it just seems like a lot of very fine-tuned. If you're going to say that gravity and temperature affects the excitement of the gas molecule, that seems like a very thin line to be able to detect.
It's just different forms of imparting energy onto something. That's all. If you give something a force, you've given it energy. If you heat something up, you've given it energy. That's all I'm saying when we talk about different variables and adding energy. Temperature is just the easiest one because we could hold a flame to something. We can hold ice to something. That's just easy.
But what I just said is why they have to call it a closed system, because it's obeying pretty much the gas laws. It's expanding up there and reaching basically a limit, okay, and it's cooling down. Like I said, if it was a vacuum, it would just keep going. It'd keep going. It wouldn't really be a change in temperature, just entropy. But the fact of the matter is, in reality, it does get colder up there where the gas is expanding to. And they act like, when I'm making this argument, they act like they say there's a gradient, just step outside. And I'm like, yeah, we can demonstrate that down at the ground. But how did the air get up there to Mount Everest? How does it get up there to 20, 25 miles? And then I show them the balloons in liquid nitrogen. The air's still up there, okay? It's just cold. Them balloons, they deflate completely, and then you warm them back up and they inflate. So to me, there is no void. And the whole all their arguments are based on starting in a void or a zero something. And all their things have to be positive. To me, it works in equilibrium. So you could call it negative, but to me, it depends. Something is only a negative if something around it is positive. You know what I'm saying? Call it what you will, but for there to be a positive, there has to be a negative. Period.
I think in different contexts you can say that. Like a velocity is always positive, but if we have a particular reference, if I run in one direction, you run in the other, it's almost like you're running negative 2 times my speed because you're going away from it. So I can call that negative even if it's not
velocity's relative. There is a negative.
Right. Well, that's kind of what you were saying, Brian. You could call it that, but
hold on a second, Brian. I really liked what you showed with the balloons and the nitrogen and the liquid nitrogen when the guy did that thing, because the gas is still inside that balloon. It's just in
all it does is lowers the temperature and decreases the pressure. That's all that happens there.
So all that gas could just still be there, but it's just cold.
It's just cold. Now, given enough cold, if it gets cold enough, it'll change states again to superfluid, and that's where the science is right now, and that's kind of where we're at. Rocky has mentioned it. I want to say, what's his name on Glowbusters? Iru made a great presentation, about, showing the instruments that recorded that right there by absolute zero temperature, and then he showed the superfluid, how it acts, how it has no friction, so things, we might be able to propel things like with just a little heat or charge up there. We don't know what's going on up there, but I don't like avoiding it. I like talking about it, man, because what we're doing now in brainstorming, this is where we get somewhere with ideas. It's fun, man.
Is there a difference between in atmospheric pressure between the summer and the winter, or say at the equator and the north and south poles?
Yeah, night and day. There's changes in pressure, just night and day. Sun's a great agitator.
It's probably similar to the tire. When you put pressure on one side, it displaces to the other. It's probably like that on Earth, where you have particular pressure in the day, and then it just gets pushed and moved to where your night, you're experiencing different pressure, but that pressure probably shifts with the sun or some shit.
I wouldn't think it would be that significant, though.
So after watching that thing with the balloons and the nitrogen, I mean, there could be just as much gas up top as there is on ground level. No?
No, there's not. There's less material.
What about the balloons? What about the balloons?
Well, it just depends on where your weak spot in the balloon is.
What about the balloons when they got cold?
Weaker in a certain area, it'll expand there.
I haven't seen what you're. I haven't seen what you're referring to. I have heard it brought up a couple times, but I haven't seen it.
Sure, let me explain.
Go to Flat Earth Test. Go to Flat Earth Test, and it's at the 4-minute mark, exactly the 4-minute mark on my video on Flat Earth Test 2 videos ago.
I'll just explain to him real quick. They have these balloons that are fully inflated. They put them in liquid nitrogen, and they shrink up. It looks like all the gas is out of them. But then he takes them out of the liquid nitrogen and heats them up, and poof, they just poof back into fully expanded balloons with all the gas.
Yeah, he don't even heat them back up. Just the room itself, almost instantly, within about 3 or 4 seconds, they're reinflated just from coming out of the liquid nitrogen.
The gas was in the balloon. Temperature alone made all this gas seemingly appear out of nowhere.
So what you're saying, Jeremy, what you're saying is, could there be just as many molecules, say air molecules, at the top of Mount Everest as there is, say, at sea level, and it's just the fact that they're less excited because it's a colder temperature?
It's a temperature gradient. Chemo used to argue this with them in GEMS, and I used to think Chemo was kind of nuts for this, but after seeing that thing with the balloons, I'm kind of towards Chemo's side on this.
Right, that's relativity. That's relative density. Everything is relative to another. So by the math, it's too complicated to do it like that, apparently. But they could do the math with that. But
wait, Brian, what are you talking about? How does that connect to the equator versus Mount Everest?
Well, it boils down to everything starting with a zero. They have to attribute everything as positive, where relative density disequilibrium is just one argument in the fact that everything acts relative to another. So there's no everything is positive. It depends on what is around it. In other words, if you start pulling a vacuum, that's a negative pressure. They won't call it a negative pressure, but it's negative to me. And so where I'm standing is the zero pressure. Where I'm standing is zero gravity. Okay, I'm not standing at 1G. Okay, I'm standing at zero. I'm standing at equilibrium, and there's no gas pressure around me. This is zero for me. This is equal. The same thing with pressure. There's no positive pressure around me. I mean, there's no positive temperature around me. Room temperature is basically zero. What you add to that, and then it's positive. You take away, it's negative. That's my opinion.
Okay,
that's extremely flawed. Because there is temperature, there is pressure around you.
So how do you have 1G on you standing there and 0G's falling when it's supposedly the very thing making you fall?
You've got 1G, which is 9.8 meters per second, which is positive acceleration. If you had 0G, you would be floating.
So you would just be equilibrized within the medium.
Equilibrized?
Yeah, I have a problem with that.
Oh, shit.
It's not going to be the last time you guys laugh at it.
If we take away the void of space, then we take away absolute zero. We take away, because they can never reach it. They never will, because there ain't no such a damn thing. It'll keep going negative. They'll keep hitting decimals. It'll never hit absolute zero. They'll just hit another decimal because they're not thinking in terms of equilibrium.
Brian, what I'm trying to argue, though, I'm agreeing with you, Brian, but what I'm arguing is when you're free falling, you're falling. So you start falling faster than the medium would allow you. If you see what I'm trying to say? If you're falling at 0 G, that's because the gravity's pulling you.
In my opinion, if you're falling, you're in disequilibrium. Period. If you're falling, to say otherwise is
he's saying that once you're at 0 G, you'd be floating.
They like to.
So if you're falling,
everything they do,
then you're going
they're
faster
invoking space,
than,
man. You hear me?
Hold on. Let me try to get my point here. My argument is, anytime you go through a medium faster than you naturally would, you're going to get that effect.
Going to get what effect?
So I don't understand how you would have. Go ahead. You guys go on. I'm going to think on this.
All right, think about it, then get back to us. I was just reading something. I've got a question. I was looking up the difference between the atmospheric pressure at the poles versus the equator. I want to read something to you. In meteorology, hopefully you guys can help me understand this. The polar highs are areas of high atmospheric pressure around the north and south poles. The north polar high being the strongest one because land gains and losses heat more effectively than sea. The cold temperatures in the polar region cause air to descend to create the high pressure, just as the warm temperatures around the equator cause air to rise to create the low pressure.
So you're telling me we have a horizontal pressure gradient?
Oh, right. It all works in equilibrium, man. That's just it. They got to everything they do. They got to invoke space and a zero negative or an absolute zero and an absolute zero pressure. That they could theoretically reach, but in reality, here on Earth and under the containment, there is no such thing as a void. There's no everything works in harmony with everything else. There's no getting around it.
Is that what that says, Brandon? Though there's a horizontal pressure
No, it
gradient?
doesn't say that, but the pressure, the atmospheric pressure. What this essentially says is that atmospheric pressure differs at different altitude. At the same altitude on different places on the Earth. But what this is saying is that the atmospheric pressure at the north and the south pole are higher because it's colder and lower at the equator because it's hotter.
Okay, like hot air rises. So if the air is hot, it's going to rise and physically move, thinning out the air around you. And if it's cold, it's going to lower, and then you're just going to have more air around you in that same volume.
I just got in a debate.
Okay, so this is what you guys would expect then. This fits in with what you guys would expect then. You would expect there to be higher atmospheric pressure at the North Pole and lower atmospheric pressure at the equator?
It makes sense to me, yes.
You would expect a horizontal pressure gradient on Earth.
I never thought about that. I never thought about that. So it's one of those things that when you read it out, I have no problem with the explanation. It's just something I've never thought about. So 2 hours ago, if you asked me, I probably wouldn't be able to give you a reply. But after that explanation, I have no problem with it.
So I've got another question just to clarify things. That 70-degree box that we had, that box with oxygen in it that we had in the 70-degree room. If I crank the heat up in the room to 90 degrees, will the pressure inside the box rise or fall?
Rise.
It'll rise. So hotter,
adding more energy,
rises. Now, if I lower the temperature, it will fall. The pressure inside the box will fall, the atmospheric pressure?
Yes. You have a particular volume. It's not being allowed to move from that particular volume. And I think I know where you're going.
So it wouldn't be dead.
Well, yeah, I'm just trying to understand. There seems to be a conflict for me, and I'm by no means I'm a total novice when it comes to this gas stuff. So I'm just trying to understand what.
No, there's a contradiction. There's a contradiction.
The only thing I'm feeling is what Jeremy said. So you're saying there's a a horizontal gradient.
Right.
That
I
sounds
just
mad
had
cool.
this out.
Well, hold on, guys.
that
Let's get an
Elijah?
answer to my question before we start moving on to other
Yeah.
shit.
What's
Why
up?
is there a contradiction between the box in the room, the atmospheric pressure increasing when I increase the temperature and decreasing when I decrease the temperature, and at the poles versus the equator, where at the poles it's higher atmospheric pressure and at the equator lower atmospheric pressure? Why is there a difference there?
What I would like to say about it, and you can get into the science of it, but this demonstrates the difference between gas pressure in a closed container on the surface of Earth versus the atmosphere and atmospheric pressure. They are not the same thing.
It's fallacious reasoning, though, man. I just got into it on
No, it
Jose's
ain't.
with Blue
No, it's
Marble
not.
Science earlier, and we were talking about the same exact thing. And he said, "Okay, Brian," he's like, "Show me on Earth where air is just rising up." He's like, "Show me that spot." And he's being all loud and shit. I'm like, "Okay." And I said, "Take the albatross bird. They stay out at sea for 9 months at a time without even hardly flapping their wings, riding the currents of air coming up from the ocean." And he just wouldn't even acknowledge it, man. He's holding two contradictory points. At the same time, it's fallacious, man. He wouldn't even acknowledge
They have these
To be fair, that's
parasailors,
Blue
right?
Marble. He doesn't even know what a container is, so I wouldn't take that too seriously.
They got these like I think I don't know. I'm just calling them parasailors, but they could be called something else. But there's these dudes at this damn, I'm being very vague right now. I gotta find the video. But the point is, these dudes are like using the parachutes to like they get a little run, and then they kind of just kite themselves up in a circular fashion on the winds, on the updrafts.
Oh yeah,
Without any
thermals.
motors, without any, they're going upward with the updraft.
Yeah,
that's not anything else.
Not a change in atmospheric pressure. That's wind.
Wind is caused by a change in atmospheric pressure. That's what causes wind.
At varying differential temperature pressures.
Nothing to do with gravity.
Different temperatures
I would
which
like to address
change
the
the
container.
pressure, which pushes the air one direction or the other as it expands or contracts. That's what causes wind, right?
No. Air is not being pushed. It's just moving.
Okay.
Warm air rises, and the cooler air is going to come in and occupy that space. And that's a system, I guess you would call it.
All right. That seems a little. Yeah, I don't understand what the difference between what you said and I said. When I said push and you said occupies the space, that something else was. You're saying there's no exchange of energy between the cold pressure system and the high pressure system?
I couldn't answer that.
Yeah.
I don't. I mean, that's good.
Does anybody want to? I never got an answer to my contradiction. No one ever resolved that for me.
Yeah,
Does
I'm
anybody have
trying
an answer to that?
Yeah, I'm trying to. There was 5 or 6 people that were going off tangents.
Yeah, that's fine.
I think the biggest issue with that is that in your container you have a closed system. You have a closed system. It's not dynamic. It's not interacting with anything else, and all you're doing is playing with temperature, and that's fine. And it has nowhere to go. It has nowhere to expand if it wanted to. It has nowhere to contract if it wanted to. It's dictated to that specific volume. And when you have the atmosphere, you have a very dynamic system in which the air that was once cool can move and heat up, and the air that used to be hot in another region, when it moves over the Arctics, it has a chance to cool down and lower and interact in that way. So I think that's the biggest difference is you have
Very
a
well put.
But if there was specified closed system versus atmosphere.
So help me just visualize this a little bit. So if I'm at the North Pole, help me visualize this a little bit. I'm at the North Pole. Let's say for some reason it's 70 degrees. Starts plummeting. 70 Fahrenheit. Starts plummeting. It's down to -70. What is happening with the air that is surrounding me during that temperature change from 70 Fahrenheit to -70 Fahrenheit?
It's losing energy. So it's losing energy, and because when it has a lower energy than your body has a higher energy. That high energy is going to move into that low energy, causing you to be cold. But yes, you're going to be surrounded by low energy particles, basically.
But the atmospheric pressure will go up.
Right.
How?
Because all of that low energy, because it doesn't have enough energy to move away from the ground. So that low energy is going to move towards the ground, while the higher energy has the energy to move away from the ground, much like throwing a baseball straight up. If you give it a lot of energy, you can throw it farther. If you give it a low energy, it's going to not go as far.
See what I'm saying?
So it's essentially all packs in around me is what you're saying, Biodual.
You're right. They got to have a positive or a not positive.
on,
They
Brian.
can't have negative.
Huh.
You're tap dancing around this
Makes
shit. Is
perfect sense.
cold air or hot air more dense? Which one's more dense?
Which one? Well, I think the better way to say it is pressure. Which one would cause a higher pressure? Which one would cause a lower
Okay, which
pressure?
one
I
has
would
a
call it
higher
density.
pressure? Cold air or hot air?
The higher pressure would be the hotter.
That
'Cause
just
you're
goes
giving it more
against what
energy,
you just
so it's more force.
told me, though.
Yeah, there's a huge
Right, but this is a
contradiction
dynamic
here.
system, though.
Okay.
If we want to talk about containers
What
that we can experiment in the lab, you're going to get a different effect in the atmosphere to a certain
How does the
extent, because we
dynamic
don't have
system-
all the variables accounted for.
Okay.
How does the dynamic
No,
system...
you have to
affect-
say the
Hold
atmosphere
on, Brian.
works different, but it doesn't.
How does the dynamic
does.
system affect this higher or lower pressure thing happening on the North Pole here?
Because you're adding many variables, like the air that you're experimenting with can leave you forever and go somewhere else. New air can come in and do something with you. You have winds, you have climate, you have all these variables that you're not at all accounting for when you have a set volume container in your living room and you're doing these experiments. You're losing so many variables.
Yeah.
Oh
I
my
don't know,
God! We can show a
seems
dynamic
pretty-
system in a container. We can
Yes.
take a 20-foot long
Kind of like
PVC
making
pipe.
a vacuum
Well,
and you don't ever
once you do that,
experience
Hold
Brian.
on, man. Hold on. We could take a PVC pipe. We could heat up one end and put the other end in ice water. If we make it about 50 foot long out of metal, and then we put some water in there, dude, you'd get air currents, you'd get weather, you'd get high pressure, low pressure, you'd have gradient. We can demonstrate all that shit on Earth in a contained
do it?
system.
Once you do that, Brian.
Yeah, there doesn't
Oh
seem
my
to be
God.
any
So you're
reason in a
denying that
closed
we could,
system, though.
oh
To
my
back
God,
Brian
man.
up, there doesn't seem to be any reason in a closed system that's, ginormous that you couldn't have high pressure, low pressure zones based on temperature. If you have different temperatures within that enclosed system, why wouldn't you have those things?
That's what a terrarium is.
Yeah.
I would say if it
Bam,
was a
thank you, Rocky.
large,
That's
if
why
it was large enough,
condensates, things can grow. Yeah, left lane. I think you're proving yourself to be, come on, man.
kiss my ass, Rocky. I don't even know what you're talking about. I don't know why you
there
pound
it is.
me all the time.
That's all
You
it
pound-
took, huh?
I didn't say a word to
you
you,
ever
but
heard of a terrarium?
yeah, that's what I was
Yeah,
saying.
I
A
hear
large
you.
enough
I hear you
system,
playing
you
dumb.
could create weather in a
So
large.
smart, but so dumb.
Yeah, kiss my ass, Rocky.
Closed system, terrarium, condenses, condensates inside and out.
That'd be a
Things can
good
grow in
that'd
it,
be a
plants
good way to
survive,
experiment.
Animals survive.
Rick, yeah, that'd be a good
The
way to
cycle of
experiment
life.
with what's being talked about here. Now, do
Yeah.
you take that terrarium, fully functioning terrarium, and now you introduce an extreme cold temperature, and then you introduce an extreme hot temperature, and then within that terrarium, you can see what happens with the pressures, and maybe you get something different. I don't know. I wouldn't make a prediction, but it'd be interesting.
Yeah, I'm still trying to wrap my head around how it getting colder increases atmospheric pressure, but your explanation made sense in a way. But
There is more than one thing going. There's more. Nah, Brendan, you're right. You are Brendan, right?
Yeah.
They're holding two
Okay, sorry.
contradictory positions.
No. I'm not talking about contradictory. I'm saying, like, when I'm trying to figure this thing out, there's not one thing going on. There's like two things going on, and it's like what you just asked right there. I wonder the same thing. Like it's like I'm trying to get some meat to chew on, and it's like I'm always left kind of unsatisfactory when this conversation is being had.
Me too. Yeah, that's why I don't bother with it too often, is because there doesn't seem to be a satisfying answers out there.
And I'm gonna tell you why. Because they're holding two positions simultaneously. Reality is showing them equilibrium around us. but their explanations have to all be positive. They have to have pressure or no pressure. They can't go in the negatives. But what we see is equilibrium. The same thing like with the ping pong ball and the golf ball argument. When I dropped it from the roof, they said, I asked him, I'm like, so why did the golf ball drop faster? They're the same size. They have the same air resistance. And one of them, I think it was left lane. It might have been somebody else, but because one's denser. I'm like, exactly. And they're like, wait, but no, it's gravity, this, that. And I'm like, their common sense has them blurt out the natural answer. But then they have to retract it. They have to hold, in all these arguments, if you go deep enough, they have contradictory reasoning, man.
Brian, on the golf ball and the ping pong ball, if you sit them on the table and blow on them, which one will roll and which one won't?
Why don't you go do it, Howard? Why don't you go do it, man?
I don't need to. It just
That's what you just told me with the other thing. I don't have to. It's common sense. Yeah, the ping pong ball would. It's lighter.
Yeah, well, it's more susceptible to
dropping them, not blowing them off a table, mate. What do you've got confusing the issue? We're talking about dropping them.
Yeah, but the whole point is things different weights, and your model drop at the same rate. It all has to do with air resistance. So the ping pong ball is the same exact size as the golf ball. It's just different densities, different weights. So the golf ball falls faster. Okay, you can over-explain it.
Sorry to cut you off. Before we get too far away from what just happened, I want everyone to keep in mind that there is a horizontal pressure gradient on Earth. Okay? There's a vertical and a horizontal one. So if they ever try to bring that shit up where, oh, there's a pressure gradient. Okay, there's one going horizontal too. How's that work for gravity?
There absolutely is. Look at the clouds, man. There's a little line at the bottom, like them big fluffy cumulus clouds. They all have like a layer that they bottom out at, and it moves around. You know, it's moving around side to side constantly.
Yeah, I didn't hear anywhere in that explanation of why there's higher pressure here and lower pressure there, what role gravity played in any of that, supposedly. Why do we need gravity in relation to this? Does anybody know?
No, I already explained it. Low energy, high energy. When the hotter the gas is, the more energy it has. Just like when you try to throw a ball straight up, if you give it more energy, it's going to go higher. If you give it less energy, it's going to stay lower. It's the same thing. It's all about energy.
So the pressure gradient on Earth has nothing to do with gravity.
No, it does.
There's a horizontal one.
Yes, we already know about the horizontal one, Jeremy. When we talk about refraction, we're talking about different density layers horizontally across the surface. It's nothing new. But if we're going to talk about a gradient pressure system, then generally, almost always, you're talking about a vertical system. It's not new, Jeremy.
And there's a horizontal one.
Yeah, and that's fine.
There's always a horizontal one.
Yeah, and I won't fight you on that, Jeremy. We already know this. But when we're talking about
that pressure gradient has nothing to do with gravity.
What do you mean? Of course it does. But it's going to have different effects across different climates and different regions, different elevations, different whether it's terrestrial or the ocean or something, or lakes. It's going to have all these kinds of effects. It's not just one variable that does everything, Jeremy. It's a multitude of many variables at different values.
All right. How does the horizontal pressure gradient have anything to do with gravity?
If you don't understand after I just said all that, it has to do with a number of variables, gravity being one of them.
Well, how does gravity as the variable affect this horizontal pressure gradient?
I don't think that you're forming a good question to respond.
We have a pressure gradient horizontally. How does
no, we don't.
Yes,
no,
we do.
Rumpus,
we just went over it.
It's not a gradient like we have vertical, but we have varying pressures at the surface level due to a number of reasons. That's what Jeremy's trying to
do. We don't have a horizontal gradient, a general one, as he's implying. We just have local effects. That's irrelevant. There's no consistent gradient. So we do not have, in principle, that's just a result of local activities. Nothing. It's not a system like the vertical one, which is consistently there all the time.
Oh, it's consistently there all the time. It's always the same everywhere all the time?
There is a consistent vertical gradient.
There is.
Yes.
So is it the same at the North Pole as at the equator then? This consistent vertical density gradient?
Is it the temperature obviously is different at the... it's still the relationship between what's going on at the bottom and the top is consistent. Whether or not because you've got a lower temperature at the poles... would mean that there will be a different pressure to that at the equator, but the change, but going vertically, will be the same profile.
Does the temperature increase or decrease generally as you go up in altitude off the surface of the Earth?
It decreases. It decreases.
Okay. So it sounds like we have a temperature gradient.
Yeah, we have a temperature gradient that goes down as you go up.
Okay.
Chemo was right this whole time. I doubted him this whole time on this.
What's all based on temperature?
It sounds like to me the density gradient.
No, the pressure gradient, the density gradient is caused by gravity.
Oh, I thought it was caused by temperature. We just went over that.
No.
Oh.
No, it's not.
Oh. Yeah, we just went over this.
So the fact that temperature goes down is not the cause.
Guys, let me help.
The density gradient is the caused by gravity, which also causes the change in temperature.
Is there a gradient pressure?
There are several factors.
Is there a gas pressure gradient, Rumpus, in a greenhouse?
Is there a... Say again, sorry?
Is there a gas pressure gradient in a greenhouse?
Vertically, yes. It's not much. But
and horizontally, but...
No, there's not horizontally. Not horizontally.
Well, hold on.
Not horizontally. Vertically
Let me
only.
say this, Rumpus. Let me say this. If you take gases and you color them, right? You color them. The densities of the gases will stack on each other, right? Within a room, a container. So there's your vertical, but your horizontal, where's that at?
I didn't understand your question at all, I'm afraid.
The level of your colors. So
yes.
If you take gas and you color it, and you have multiple different types of gas, right? They'll layer on each other like liquids. So
well,
there's what you're saying.
Well, no, they mix. I don't know what you're
talking about. We're saying the horizontal is, hold on, where we're saying the horizontal is the layer.
What?
The layer of the gas. So when you're in a greenhouse, right, which requires a container, you can have gas pressure gradient. It's all based off the heat source.
No, it's not.
Well, that's a good point.
Yes,
James.
it is.
Let me ask a question. Set something
yes,
up, Rumpus. So
no,
let's say I've got a 100-foot tube, and I fill it with oxygen, and I heat the bottom of the tube up to I don't know, 80 degrees Fahrenheit, and the top of the tube is in negative 10 degrees Fahrenheit, and it decreases linearly from the bottom of the tube to the top of the tube. What is going to happen to the atmospheric pressure inside that tube from top to bottom?
Right. Well, because gravity is in effect, you would get diffusion of the gases. They will mix up in the usual way, and then and the temperature will do the same eventually, and then you'll get the normal temperature gradient. So, obviously, if you kept one end, if you actually put something at the bottom and said this is going to be 80 degrees, and you put something at the top to be minus 10 degrees, so you're fixing the temperature gradient there, irrespective of what the atmosphere does.
I'm fixing the temperature gradient. The temperature gradient is fixed. It's linear from 80 to negative 10 at the top.
Well, you can't you can't guarantee the linearity of it. If you make one at the bottom, at the top, it doesn't necessarily mean to say it's going to be linear in between. All you can do is fix the 2 points.
No, I'm telling you in my hypothetical that it's linear from the bottom to the top.
Well, that wouldn't exist in reality. Physics would not allow that. But
you just told me earlier that there is a temperature gradient on Earth.
There is, yes.
So why couldn't I create a temperature
actually, in saying that, sorry, I was thinking of pressure. The temperature actually is close to linear, actually. Yes, it's the pressure and the density that are curvy. So, yes, in fact, you can have a linear temperature gradient, because that's what happens in the atmosphere. Basically, it's a linear for every, so many 100 feet you go up, it goes down by a degree or something. So yes, actually the temperature is linear, but the density and the pressure are not. So what's the question again, sorry?
Okay, so the pressure inside the tube is based off temperature, right?
No, it's based off the height, because the gravity causes the change in density.
So now pressure isn't determined by, doesn't change the atmospheric pressure. Is that what you're telling me?
Oh, in this container, is it closed at the top and the bottom?
Or
is it just an open thing? Well, if it's open, then
if it was open, it wouldn't be a container, Rumpus.
Okay, well, I was just checking, but he didn't know what he's saying. It doesn't matter.
Okay, let's say it's closed. Let's say it's closed.
Right. Okay, which means that then you're still going to have the gravitational effects. You're still going to get a density gradient in there because gravity will mean that the stuff at the bottom is denser than the stuff at the top. And if you're holding the temperature, at a gradient, then you're going to get a linear thing. So what do you want to know?
How's the pressure going to change from the bottom of the tube to the top?
Right, the pressure will be greater at the bottom than it will be at the top. Okay, you got two. If you're holding the you've got two effects there. You've got a temperature gradient which will affect the pressure, but you've also got gravity. I suspect that you've got such a big temperature gradient between those two that would be dominant, and therefore it would actually be lower pressure at the bottom than top, because you've got such a high temperature gradient. And this is what we see with ephemeralages, of course. The ground gets so warm that that increases the temperature of the air next to the ground, which means they become less dense than the air than they normally are on the atmospheric temperature density profile. So in fact, they do become less dense. So yes, your example, you would have less dense air at the bottom than you would at the top.
All right, I give up. Go ahead. Anybody else wants to play?
But normally, if the ground in the atmosphere was not heated, then you would get more dense and warmer at the bottom. But the way you've worked it there, you've made it, and it would be linear. But the way the temperature gradient you've given would mean that in fact it would be less dense at the bottom, as though just like on a sunny day, the ground is warmed up and therefore gets hotter.
Hey,
So
Rumpus, if I dip a balloon in liquid nitrogen and the whole thing deflates and there's not a drip of air detectable, is there still air in that balloon?
Well, yes, it's turned into a liquid, hasn't it? So what you're saying, you put a nitrogen balloon full of, sorry, did you say nitrogen or air? I can't remember now.
No, I take a balloon. I take I take a balloon about the size of a basketball.
Yeah.
And I put it in liquid nitrogen, and it completely deflates.
Yeah.
And then I take it out of the liquid nitrogen and let it sit there on the table at room temperature, and it reinflates. When I first dip it in and it disappears, is the air still in there?
Yeah, of course it is.
Okay, same thing up at high altitudes. The air's still there. It's just cold.
Yeah, it's less dense though. The way the air, there's also the density of air is less as you go higher because of gravity.
Because of temperature, okay?
If you
hold on.
You increase the density.
Just think of this hypothetically real quick,
if you decrease the temperature, you increase the density.
I understand that, but listen.
So it does the opposite of what you're saying. Hold on. Listen, Brian. Listen. The air at the top of the atmosphere is very cold, yet it is less dense. That should tell you it's not following that rule you've just described.
Okay, then let me ask you this. Okay, if the air is being created at the ground and it's expanding up into the atmosphere 20, 30 miles, would the air expanding? Would it cool everything down? Would it make everything cold?
We don't have
how ACs work.
We don't have that happening. We don't have great wads of air being generated at the ground level. Where do you get that idea?
What are you talking about, man? We look at birds over the ocean, okay?
They fly,
They ride the currents. Hey, I just looked it up. An albatross can stay out the ocean and not flap its wings for 2 years from the air coming up off the water.
That's a horizontal wind. That's horizontal winds. It uses horizontal winds to do that, not vertical ones.
Okay, now how about this, Rumpus? How about this? If, just say hypothetically, if all the air was being created at ground level and expanding up into the atmosphere, wouldn't it cool down?
All the
yes, it would. Yes, it would, but we don't have that, so it's irrelevant.
Yes, it would, and yes, it does. And
no,
the
it
birds
doesn't.
ride the
If you had the ground or air coming from the ground at the rate required to keep the pressure gradient, it would be a supersonic, massive wind that you would have. It will blow you up at the top of the atmosphere to do that. If it would try and equalize the pressure. The only reason it doesn't try and equalize the pressure is because of gravity. What a ridiculous idea!
No, that's only if it was an open system in an endless outer space vacuum. Then it would be explosively going in all directions.
No, we've got a pressure difference. Hold on. We've got a pressure difference. On Everest, it's 1/3 the pressure. Hopefully you've seen the demo that the Flat Earther loves about the bromine moving into granite. I'm in the middle of a sentence. Brian, I'm in the middle of a sentence. You've seen the demo. Brian, I'm in the middle of a sentence. I'm in the middle of a goddamn sentence, Brian. So we've seen the demo of the video of which we've got some gas and bromine on one side of a chamber, then on the side of the near vacuum, and they open up the chamber, you go zip. That's what would happen if you. Would happen with the air at the ground level, which is Everest is 1/3 the pressure at ground level. If there wasn't gravity there would be a near instant disappearance of all the dense air near the ground and high pressure air to Everest. Finished. Jesus Christ,
Hold on.
you two.
Let Arwen go. Let Arwen
Well, I thought Brian was next, actually.
I ain't even make my
let's
point,
hear
man.
about helium rocks again.
One other thing, man. One other thing. If it was a vacuum and the air just rushed into the vacuum, there would be no change in temperature, and it'd just be a change in entropy, dumbass. There ain't a vacuum up there. There's got to be a container. The air would keep expanding.
No, it doesn't.
Rumpus, you should draw us a diagram of this.
This one probably. Well, yeah, I could actually. I could draw a diagram of Everest and the pressure, and this idiotic idea that there's something generating enormous. I mean, just imagine how much it'd have to be continuously. I mean, this is just contradicted by the existence of still air.
We don't need
today,
your
for instance,
incredulity taking up the airwaves.
No, there is no massive airflow from down here up to the level of Everest. Therefore, the whole idea is ridiculous.
Could I get Brian to kill his,
so we can
or
see this
Dave
visually?
to kill his camera, please? He's killing my audio.
Let's get a diagram going, Rumpus, so we can see
mine
this
too.
visually.
It's killing my audio too, y'all.
Okay, I could show you a diagram.
What's wrong? What's wrong with audio?
James's camera is killing my audio.
Oh.
I don't know if it's his camera. I don't know if it's his camera, but something's messing with my audio too.
I wanted
I'll
to
turn it
mention
off.
that
I don't see why it'd be the
wind is for whatever reason forgotten about as, also a part of this atmos, right? And it's actually going sideways. So it's another vector that's not down.
Not relevant.
It's not?
Sure it's not.
No.
Sure it is.
It's just local effects.
Local? Isn't there a global
where
weather
else
system,
is this
supposedly?
Where else is the weather at?
What are you talking about locally?
It's just a local. We're talking about general, wide-scale effects. We're not talking about some little local wind.
Yeah, there's weather and wind everywhere on Earth, Rumpus.
Yeah, but it's irrelevant to the. It doesn't. The wind that we're talking about is absolutely the sort of local wind has been nothing like the wind that it would be if we didn't have a gravity that would go from the surface of the Earth to
all of the local wind,
to Everest.
all of the local wind everywhere is going in lateral direction.
See, the problem is you're not asking Rumpus the right question. Rumpus, how long is this local thing for?
Well, the
point is he's trying to separate. He's trying to.
Hold on, Elijah. We're getting a lot of feedback
it.
from your mic for some reason. It's
Can you stop rubbing the bloody phone on your leg? Jesus Christ.
Rumpus, how long is local? I want 10 miles, 1 mile, 10 feet. How long is local?
In comparison to, it doesn't matter whether it's 10 miles or 100 miles. That's still local in comparison.
Red herring, it doesn't
to the
matter
effect.
because
But
all that
still,
we're talking
Jesus,
about is
crackle on
air
your phone.
Is it 1,000 miles?
Well, that's still a bit local, yeah.
10,000 miles. Is that a little local?
No, that's not local. But you don't.
5,000.
That's not local.
Playing the Price is Right with you. How about 6,000? Is that
No,
local?
that's
Jeremy,
not local.
Jeremy, a better question for Rumpus would be, hey Rumpus, have you ever looked up the it's called the list of unsolved problems in physics? Have you ever looked it up?
I have looked at that occasionally. I think there are about 10 big ones.
So you might want to go double check that and then get back to us because you're trying to explain a problem that is unsolved.
Which problem is that?
You tell me.
Okay, well, I don't
The
know.
problem that
If
you've said
you're not
that
going
you
to
looked
talk in
up
code, I'm not going to bother with you. I was just going to show this.
I just tuned in. So
well, okay,
Rumpus, if you looked him up, and he brought it up
I
based
have no
off
idea
what
what
you're
he's talking
talking
about. And I don't care if he's going to talk in code. I'm not going to bother to talk to him. Right. So here's this graph of the temperature change against and pressure and density against altitude. So we've got the height in meters on the left-hand side, and we've got 1 being the situation at ground level, and then we've got fractions of that as a percentage, 0.9, 0.8 of that. And so you can see what temperature does with altitude, and then here you have density and pressure.
Hold on a second. Hold on. Your diagram's missing the horizontal pressure gradient we have.
There is none. There is none. It's not relevant.
Yes,
You still
there is.
answered how much pressure was in the balloon that deflated when we dipped it in liquid nitrogen. How much pressure did you measure in that balloon that had like 3 psi until we dipped it in liquid nitrogen and it deflated?
3.
How much pressure was
Why
in
was
it
it only
then?
3 psi? You was sure it'd be 14 at least. Why do you use only 3? You can't have a balloon with less than.
Just answer the question, dude. Whatever you want to call it. What happened? What's the measurement? What's the new measurement?
Well, it would become, if you put it in liquid nitrogen, then the nitrogen and the oxygen would both become liquid. So there'd be, I can't remember what the scale factor is. All the gas in there, the argon wouldn't become liquid, but the oxygen and the nitrogen would. So the vast majority of the gas in that would become liquid, which is a factor of a change in volume of about. But then again, the balloon would collapse as well. So it's a moderately complicated calculation. But I think the change in volume between liquid and gas phases is something like 10,000, I think. So it'd be. But then it would be a minimum. So it would turn to liquid. So it'd be just the change in the volume that goes from gas to liquid. So I don't quite understand why you're interested. The pressure would be, and the balloon would go down until it matched air pressure. So in fact, the pressure.
Who said the balloon had oxygen in it, man? Who said the balloon had oxygen in it?
You said air. I thought you said air in it. I thought this was a balloon filled with air.
But I didn't. I said a gas, but it could have been helium. It could have been. You automatically turn it into a liquid. It deflates completely.
Oh right, if it's helium. Right, okay. If it's helium, then they wouldn't turn into liquid. Yeah, I didn't realize you weren't specific. Right, if it's helium in this balloon, then it would not turn into a liquid, and therefore it would just simply be reduced by. Because unfortunately we've got a container here that can. Well, it was going to match the pressure. Oh God, I'll have to. It's just PV is equal to nRT. So we've got the same number of molecules. We've got the temperature's gone down by a factor of about a half because it's liquid nitrogen minus 180. Which is a 250, 273, so it's about 2/3 of the temperature. So but the balloon will collapse in on it. It'll occupy 2/3 of the volume that it had before. If it's a helium balloon, it would occupy 2/3 of the volume that it had before you put it in there. But if it's nitrogen or oxygen, it would turn into a liquid, and therefore the reduction would be much less, and there would actually be no gas. No gaseous except for argon.
Okay. What if you didn't have a volume?
Hey,
what if you didn't have a volume?
We defined a balloon, which is stretchy, which means it'll like to go down to a very small size.
I don't care if it's a balloon or what it is.
It makes a big
what
difference.
happens if you don't have a volume?
So if you just reduce the temperature of a system without a volume, well, obviously, in something like the Earth's atmosphere, we've got gravity pulling the atmosphere down to the thing. So if we change the temperature down to,
are you saying that the Earth's atmosphere does not have a volume?
If there's no volume,
but it changes.
There. If
It's
there's
not
no
fixed.
volume,
What happens
there.
if there's no volume? Is the question.
Well, that's
There's
ridiculous. Well,
nothing
gases
there.
have. Well, that's not. Well, but if you're saying that gases don't have a volume, then they don't exist because they do have a volume. All atoms have a volume.
What's the volume for Earth's atmosphere then?
I know that off the top of my head. I think something like 10 to the 24 cubic meters or something.
I want to get a
So there's
clarification on something, Rumpus. You said that if the atmosphere was created at ground level, if the gases were created at ground level, there would be huge movements of air up or of
Without
the atmosphere.
gravity. Without gravity. I think the scenario was described.
Why are there not huge movements of air up
Not
to the town of
vertically,
Mount
no.
Everest? Huh. Because
Not vertically. Nothing.
Mount Everest
Nothing in comparison to.
is one of the
Nothing in
windiest
compar-
places on Earth.
Yeah. And that would be nothing. Absolutely zero. If you didn't have any gravity, we've got this massive temperature pressure difference between ground level and Everest, and it would be the wind that we would have would be supersonic, probably.
Yes.
Going from ground level to Mount Everest, so you'd have the most tremendous winds we've ever had, and the whole
Not if
of
we had containment, bro. Not if we had containment.
We don't have any containers between us and Everest, you idiot.
No, I mean above Everest, dude.
Yes,
it
but
wouldn't
it-
take supersonic winds to get a couple
would.
miles when the wind's expanding up 25
Brian,
miles, dumbass,
there
with a
would be
container right
nothing
above
without gravity. There would be nothing
You're sitting
stopping
here
the wind.
telling
The
us
pressure.
how all this gas is contained
Can I
to
just
the
finish my
Earth.
sentence, James? Can I just
and
finish
how
my
it
sentence?
doesn't go
James,
into
can I
space.
just finish a
Now you're
sentence I was in the
saying
middle of,
there is
please?
no container?
James, could I finish my sentence to Brian? So, Brian,
go
if there
ahead,
was
shoot, let me
nothing,
hear you.
there's nothing in the way of the air between the ground level, ground level than Mount Everest or equivalent height anywhere around the world. So there would be a huge, vast, supersonic movement of air at high pressure down at ground level to 1/3 of its pressure at the height of Everest.
Why?
The reason that doesn't happen is gravity.
Why would there be this huge supersonic movement?
If it was an infinite void, then there would be a supersonic gas racing off into space, man.
Hold on a minute. Why would there be a huge movement?
Because we've got a huge pressure difference. We've got 1 atmosphere at ground level, and we've got 1/3 of that at Mount Everest.
That's what we currently have. What the fuck does gravity have to do with
the only
it?
thing that can account for that is the gravity. If there's no gravity,
why?
there would be a huge wind.
How would you get?
And Brandon,
how would you
get a
get
couple
the gradient
minutes
without
to
gravity?
Rumpus, please,
Air
guys.
at high pressure goes to low pressure. That's why I was talking about that.
Look into comedy.
Brandon, please.
Well, that's probably why Mount Everest is one of the windiest places on Earth, I would imagine.
The pressure would equalize, Brandon. And it
The pressure will never equalize because there's always temperature differentials on the face of the Earth. The pressure is never, ever going to equalize. What's your point?
Yes, it will.
Let Brandon get a couple minutes with the Rumpus, please, guys. Everyone control themselves.
Gravity is theoretical physics, not experimental.
Go stand on some scales, idiot. And you'll see a measurement of the gravitational force in your body in front of your face. What a moron.
Rumpus, if the universe is an infinite void and there's no container, that's when the air would rush off at supersonic speeds, jackass.
Incorrect.
Molecules have the force of gravity pulling it to Earth. Gee, just like you on your scales. The same force that's pulling you down your scales and registered on your scales in your bathroom is exactly the same force that's exerted on the molecules of the air.
So it all boils down to gas going down in a vacuum chamber. And did you hear my little experiment?
No, I missed that.
We're going to take a bell jar or something maybe a little bit taller. And
Hold on, did you just say gas in a vacuum chamber? You do realize there's a contradiction there, don't you?
Yes, I do. But you do understand that we can start evacuating the gas out of a chamber until the sound goes away completely.
Right.
So we wait till the sound we wait till there's only like just 1/10 of a decibel of sound where we could barely hear it, and then we put an alarm at the top and at the bottom, and we let it settle. But you got to give us a time scale on how long it takes for the air to run out of energy and drop to the bottom, so we could see if we get louder.
Well, hold on, it won't do that.
Can I address something,
air
Rumpus?
would drop to the bottom of a vacuum chamber.
No, why would it do that?
Can I address something, Rumpus?
Because of gravity.
Incorrect.
Can I address something Rumpus just said? What's the contradiction? Rumpus, what's the contradiction about gas in a vacuum?
Well, you can't. It's not a vacuum if you've got gas in it.
So no vacuum's ever been made on Earth. Then you're telling me?
No, he's putting gas
Walk
into a
yourself
vacuum.
into a really tough spot.
Hold on,
here.
just try and listen. Let me answer, Jeremy. He's just talking about putting gas into a vacuum chamber. If you put gas into a vacuum chamber, it's no longer a vacuum chamber.
So if there's ever a vacuum
you got to
chamber,
get any noise at all, you need some air in there, bro.
There will be. Why do you think that the gas?
I did not say it would still be a fucking vacuum, Rumpus. To get any noise, we would need a little bit of air in there, dude.
The pressure gradient over the height of a vacuum chamber is almost undetectable. It is detectable. That's how, in fact, altimeters work, and we can detect the difference between and if you put a very sensitive barometer at ground level and you move it up just a foot or so, it can actually tell you that it's done that just from the change in gas pressure. But it's very small.
Rumpus. So any vacuum chamber that ever has had gas in it is not a vacuum chamber.
Yes, I mean if you put gas into a vacuum chamber, it's not
so
a
we've
vacuum.
never made a vacuum chamber.
But you don't put gas into it; you extract gas from it. The whole point of making a vacuum
if there's ever
is you
gas
remove gas.
If there's ever gas in a vacuum chamber, then it's not a vacuum chamber anymore, right?
Why are you putting gas back into a vacuum chamber? You just simply would get the vacuum pumps going until you get the pressure you want, and there you've got it.
That's not what I said. I said take the air out and keep taking it out until there's a tiny bit left.
Okay,
to where we
fine.
get a tiny bit of sound, just a tiny bit of sound, and then we put an alarm at the top and an alarm at the bottom. I know you're talking about the barometer outside the vacuum. You know,
it's so small. The difference in pressure between the top and the bottom of a vacuum chamber, unless you've got one that's a few miles high, will be almost nothing.
Wait, I want to make a video. Say it again. So air molecules do not go down.
They accelerated down, but they then bounce up again. That's just imagine you had some bouncy balls that were running around at.
No, don't go through the whole thing. Don't go through the whole thing. Don't go through the whole thing.
It's just the original.
Don't go through the whole thing. Don't go
Why can't we
through
talk
the
about
whole
bouncy
thing.
balls?
Right. So
why don't you want to talk about bouncy balls?
I don't want to go through the whole thing again. Just
here we go. Because remember, the thing to remember,
guys.
the thing to remember that you're not getting is that the gas molecules are running around at 500 meters per second.
Will the
So
gas
they're being-
eventually settle down and
Can I just
fall
finish a
to
sentence,
the
Brandon?
to the
Can I just
ground?
finish a sentence?
Rumpus, will that ever
No, I want
happen
to
in
finish
the
my
chamber?
sentence.
Yes, an absolute zero.
I would like to finish my
Okay,
sentence.
if I keep the box at 70 degrees, Rumpus, if I have a box in a room and I keep the entire room at 70 degrees Fahrenheit, and I fill it with oxygen, and the oxygen's also at 70 degrees temperature, or 70 degrees Fahrenheit, never changes. Will the gas ever lose its energy and fall down to the bottom of
No.
the chamber?
No, we'll all be going around about 500 meters per second.
Will it ever slow down?
Rumpus, you just
Will it ever slow down, Rumpus? Yes or no?
Does not
Thank you. If people wouldn't interrupt, I would have heard the
Because
answer.
the temperature's telling you how fast the gas molecules are moving. That's an exact link.
Right, not the gravity. Not the gravity.
Yeah,
the
well, so-
temperature.
Yes, temperatures determine how fast things are going.
Temperature
correct,
tells you how fast the gas is moving. What's wrong with that? That's exactly
Brandon-
correct.
No. Hold on a minute.
Brandon, can I mention something here?
Then what effect on the gas is
I've
the
been
gravity
trying to jump
having?
in
So it's at 70 degrees. I never changed the
Can I-
temperature. You say that the gas will
Cooling
bounce around
the
at
gas
the same
down.
speed.
Okay.
Constantly forever, it sounds like. So
before you guys
how
go
is this
round and round,
how is
can
this
I say
force
one thing?
playing on the gas? Hold on, Elijah. How is this force
I'm
of
explaining
gravity
to
of
you.
yours
Right, here we
playing
go.
on the gases inside the
Explain
box?
to you. Right. So imagine you threw a ball up. Imagine threw a ball up at 500 meters per second vertically. It will go up to about 100 kilometers before it came to a stop, and in effect become cooler. Its kinetic energy is being turned into potential
We're
energy.
talking about a
So
box with air in it.
I know, and that's why in a box it doesn't go down because it hasn't had a chance to use up its kinetic energy and convert.
You
'cause
just
it'll
told
hit
me
the
it
side
would
of the
keep
container.
at the same speed, 500 miles per hour, forever.
Yes, because it's a 70 degrees C. But if
So
you
it
throw
sounds
a
like
ball up,
temperature is the only thing that determines how fast the gas moves.
it's an
That's correct.
indication.
Okay,
No,
thank you. So gravity has nothing to do with it.
Listen, let me stop trying to
No,
censor
gravity
you,
has a
man.
lot to do with
Be
it.
quiet.
Didn't sound like it to me.
Right. So the temperature is an
I don't think you
indication of
guys
temperature.
realize what Rumpus
Jesus
just
Christ,
admitted.
James,
Like
can you be quiet?
two minutes
Let me
ago.
answer Brandon's point. So the reason you don't get a loss of temperature as a result of going up is the container's so small. But if your container was 100 kilometers high, a gas molecule that went to the top would lose a lot of its velocity and effectively, like a ball, come to a stop and then go back down again. And the temperature, you seem to think the temperature causes velocity.
You'd never
No.
get a change in temperature in the putting air back in the vacuum, bro.
5 more seconds. Temperature is an indication of the velocity. It's not the other way around. Velocity gives you temperature. So you don't have the temperature's not causing the velocity.
They're relative.
Oh, really?
They're
Now we
relative.
kind of have a chicken and egg thing, don't we here? Rumpus, how do you know that it is the gas speed that's causing the temperature and not the temperature causing the gas speed?
Because temperature is a measure of the velocity of the gas molecules. It's by definition.
Both.
It's defined. If you go and look at all the physics papers and things, I can give you the equations for what
I
temperature is.
told you, man.
The
They have everything
temperature
you
is
said is
determined-
positive, 0 to positive.
Temperature
That's,
is
in reality, everything's relative. That's why you have so many contradictions.
Somebody was asking to talk, Brian.
Let Elijah go.
Yeah, Elijah, go ahead, man.
wants to-
Okay, so what I was gonna say is like they always false us into these like duopolies, like who says that everything goes up and down. Like I said, wind moves laterally, right? And he said, well, locally, except when we're talking about nutrients being spread from the Sahara to the Amazon, which is 1,600 miles in between. Why is this? Oh my God, is that local for you?
It's just
That's why I was
ridiculous.
trying to
It's
pin
got
him down
nothing
on
to
a
do with
local
discussion at
distance.
all.
What does he mean
Yes,
locally?
we know we
man?
have
The wind
wind,
goes all the
but they're
way
not
across the
relevant.
earth.
We have a consistent.
What do you
density.
mean? Is wind air or not?
Yes, of course it is, you moron.
Does wind have a vector or not?
Yes, of course it does.
So then how isn't it relevant? We're talking about air and we're talking about vector.
because they vary randomly during a period, whereas we're talking about the consistent change in density and temperature vertically, which is there all the time and caused by gravity.
Randomly, huh? It's not determined.
Yeah,
the vector and the magnitude isn't determined by anything, huh?
They're caused by the sun and the moon.
Okay, when I say randomly, I mean it is determined by the weather conditions, but you can have a wind blowing one way and a wind blowing another way, whereas there is a consistent change in density and temperature in the atmosphere.
Let me tell you guys what Rumpus just admitted to 2 minutes ago. He said that if you took a very sensitive barometer, you could put it on the ground, raise it a foot, and it would be able to tell you the difference, right?
Correct.
Okay, what is that barometer measuring?
Pressure.
Okay, what kind of pressure?
No, God.
What kind of pressure?
Atmospheric pressure. Atmospheric pressure. Atmospheric pressure.
I don't detect any. I don't.
Okay, hold on. Let me get to my point now.
Okay.
It's measuring gas pressure because that's the atmosphere.
Yeah.
Atmospheric pressure.
Can we get on the same page? What is the definition of gas pressure?
What is the definition of atmospheric pressure?
Well, gas pressure is defined by the number of molecules hitting a particular, the momentum of gas molecules per unit area. That's how it's defined. That's what gas pressure is.
So it requires a container.
No, it doesn't. There's no container required.
Arwen's next.
I mean,
Arwen's been trying to get in.
Hold on.
In the middle of a room.
Rumpus, I know how you love to screen share. So screen share the definition of gas pressure.
Screen share the atmospheric pressure. How about that?
Also, real quick.
I don't care what you could call it atmospheric pressure all you want. The air we breathe is a known gas.
The pressure gradient drops and rises miles at a time following the sun.
The air we breathe is a known gas. So you can call it atmospheric pressure all you want.
Yeah,
It's
but
still
atmospheric
gas
pressure without a container.
Can we let Arwen
it's
get in?
not.
He's been
It's
trying
contained.
to speak for a minute.
It's not going off into space,
No.
is it?
So
even in your ball,
it's contained by gravity. Yes, by gravity. Thank you very much.
Arwen, go ahead.
Okay.
Yeah.
Oh, you're too low, Arwen. You're really low for some reason. You can't hear you, Arwen. It sounds like you're really far away.
Low, yeah.
Arwen, we can't hear you.
Then making it cold
Arwen, we can't hear you.
or not cold. Will it rush in quicker or will it?
Oh my gosh.
Arwen, your mic is
I
super
think he
low,
pushed
bro.
play on one of his videos and don't know it.
Oh, maybe. But he's
I thought
talking
he was
about
trying
the
to
same
talk.
subject.
Yeah, that is kind of crazy.
Okay.
This library.
Somebody's fucking with us.
So I think James, I don't know where he was going with that argument. No offense, James, but this gas pressure versus atmospheric pressure. I want to ask. Well, hold on a minute. I want to ask one clarifying question. I think this might be what you were getting at. So, how do you measure gas pressure? Is that what you described? You have a sensor, right?
Yeah.
And what does the sensor measure?
Measures the pressure on it.
And and when you measure atmospheric pressure, how do you measure it?
Same thing.
So
there's no
same
difference.
tool? Same tool?
Yes, there's no difference.
So you're measuring the same thing.
Yeah.
But you're calling them two different things.
I'm not. I've
Okay.
never called them two different things.
Are they two different things? I don't understand.
No, they're the same thing.
Okay. I guess we're not
But now
arguing.
they're going to say that you need a container, though.
Why?
But the definition,
Because the definition, they're going to say the definition of gas pressure requires a container.
Hold on, Rumpus. If we had air in a,
it's the antecedent.
No, it's not.
No, it's
You just
not.
made that up.
Rumpus,
You just made that up.
If we took away half the
I
atmosphere,
could take
would the
an
pressure go
antecedent.
down, or would the height of the atmosphere go down?
Hold on, I could declare that it's an antecedent that flat earthers have got an IQ less than 100. Does that make it true? You can't just say it's an antecedent if you're just making it up. Sorry, what was that, Brian? What were you asking me?
You can't have
If we
gas
took away
pressure
half the
without
gas,
a container.
Yes, you can, because a container
No.
exerts a force on the molecules to keep them in one place, and so does gravity. Gravity does the same thing as a container.
No, see, if gas hits something, it bounces back.
Yes,
But if
and
there's nothing to
gravity-
hit, It just keeps going, Rumpus.
Right. Now you need to very carefully listen to what I'm about to say.
Get that, Rumpus?
So if I throw a ball up in the air, it'll keep going?
To say to James, do you understand? Just like you're being pulled to the ground, and that force is registered on the scales.
I'm not being pulled to the ground,
thing.
Rumpus.
The same. That's how your scales
That's
work.
all I
That's
can
exactly
I'm in the medium of
thing.
air,
The
Rumpus.
same thing happens
is
to gas
all I
molecules.
understand,
If you like,
I'm not in
James,
water,
you
I'm
can
not
think
in
of them
mercury.
as having little
I'm in
springs
air.
on them. You can think of the gas molecules having little springs on them, being pulled to the center of the Earth. With that, so therefore they're being contained by a force in the same way as a container exerts a force on gases. Gravity exerts a force on the gases to keep them.
Let me say this on my behalf, and then I'll be quiet.
It's not a story. It's how it works. How do you? Someone explain. Someone explain the gradient to me without using the word gravity, please.
Gravity is a non-experimental theory of physics.
No, gravity is a real thing. Gravity
You
is a
want me
real
to
thing.
explain the horizontal gradient or the vertical one?
The vertical gradient.
Oh, what about the horizontal one?
The horizontal gradient.
Of course, why are you guys denying the horizontal pressure gradient we have on Earth?
The horizontal pressure gradient. Talk to me about the vertical gradient, though.
You guys, this whole time, you have not had Rumpus prove anything that he says. You just let him spew his bullshit.
And then they go on to the next question.
Who's talking? Is this Aether Band guy? That's no proof anything?
And I'm told to be quiet.
I know you just don't can't deny, Travis.
Love that the Aether Band guy says.
I actually made a pertinent point because everyone's talking about up and down, and I'm talking about how the air goes in all directions.
Right. That's
Namely,
weather.
another one that we experienced.
That's just
denying weather. You mean weather pressure gradient?
No, I'm not denying weather. I'm just saying it's not relevant to the discussion. There's a
by the way,
What's
the major?
Hold on. If we took away half the air instantly, would the Kármán line drop? I mean, would the gas level drop, or would the pressure go down? Which would happen?
The pressure would go down.
Why are you asking a question about something that's never going to happen? Stop doing this.
What do you mean? What? Shut up, Travis. He's doing a thought experiment. That's perfectly
thought experiment. Fuck your thought experiment. That's
you
what
just
your
wanna,
bullshit
you don't want to think.
built
I love how the Aether Band guy talks about proof.
Yeah, he doesn't. You don't want to think.
I'm leading him, Travis.
There's nothing wrong with
him.
thought experiment.
I was leading him, dude.
Yeah, you're leading him
easy
to
to
La
lead.
La
He'll
Land.
answer
You're leading him to
anything.
Narnia. Go on.
He'll answer
Hey,
anything.
someone, I asked a question about the vertical pressure gradient without.
So Travis doesn't want to think. We
All right.
Just everyone calm down, please.
Peyton Nasa, Shell, and Rumpus are muted now. Appreciate your
I mean, I listen.
contributions.
I tried to stay silent, but that last time where he called out James on the antecedent, right? He said, "Oh, then I could just make up an antecedent." No, see, you guys, there's a difference between James's argument from logic and Rumpus's argument from stupidity. Antecedents as prerequisites mean that you cannot have B if it's dependent upon A. Okay? So just because Rumpus says, no, it doesn't mean he's right. That's when you stop the discussion, have a debate, and get all your weapons out. James says, let's just say, that gas has gas pressure's antecedent is a container. And then Rumpus says, no, it's not. Then you've got a debate right there. You should stop the show and not do anything else, but let those two guys prove their
Travis,
case.
Rumpus called gravity the container. He
No
called
need for that.
gravity the container, so I tried to chime in real quick. And gravity is a non-experimental theory of physics. Just to try to get
I
Rumpus's
get that.
level.
I
But
get that.
we all know this, but he's going to skip right over that. And like you just said, say that.
Plus, you got to ask questions outside the box.
He
'cause
can
there's-
actually hold this gravity container.
No, Brian,
What
you
he's gonna
don't
do.
ask questions.
Yes, listen, Travis, there's citations for half the bullshit he says, dude. There are citations to back it up, so I got to ask him questions outside the box to get him stuttering and then lead him up to some shit and show him how his thoughts are incorrect.
I just can't figure out why they're trying to.
If you are trying to do a reductio ad absurdum, then by all means do that, but it's only based on his claims, right? Don't do the thought experiment and go outside of the box if he didn't make that claim, because then that's a straw man. So you have to stick to his claim and just take his claim to its logical conclusion.
Yeah, I understand what you're saying, bro. I definitely understand what you're saying.
I just don't understand why they're denying this horizontal pressure gradient force.
Well, I don't know about the horizontal.
That's
pressure
where I was
gradient,
going with
but
that.
as far as the
Somebody
wind,
come in and said there's
well,
lateral
okay.
wind. That's why I brought my argument up. And
I at
he
least
brought the
waited for
barometer
Jeremy to
up
finish,
himself.
James. So all I'm saying is, when he says weather is irrelevant, no, it's not, because we're talking about up and down, like that's the only thing we experience.
For everyone
You guys,
wondering
even
about
when you
why
drop
up, why
things, all flat earthers seem to forget this. They seem to forget even when you drop things, depending on, you could have the same variable and change its shape, and depending on how high you drop it from, if you drop it chest height, you get a certain result. If you drop it 10,000 feet up, you get a much different one.
Yeah.
So people they just leave all that out, just blow right by it. You can have a piece of paper fall left to right. Take the same piece of paper and you change the shape of that variable by crumbling it up, and it falls straight down, depending on how high you drop it from.
And the medium. And the medium.
The thing is, there's a
That's the
horizontal.
most important.
There's a horizontal pressure gradient force that is somehow linked with Coriolis. I don't really get it because we just started looking at this, but you know, that's a thing they're going to have to deal with. Why is there a horizontal pressure gradient force?
Yeah, if you contact
only up down.
Contact the Hoover Dam.
Your mic's still super low, Arwen.
That's what I asked Blue earlier. I said, okay, no, I asked Bob this. I said, if you take a 20-foot, hold on, if you take a 20-foot long pipe, right?
Horizontally, that's not a gradient. That just means.
There you go. We hear you
Arwen,
now.
can you hear me, Arwen? Because your mic is so low.
Other forces stop being applied.
Arwen, can you hear me?
Happening horizontally. It's just a.
Somebody else talk to him. I don't know why he can't hear me.
Arwen, can you hear Brandon?
I don't think that's Arwen. It might be a
Hold
video.
on, hold on.
I think he's got some computer issues, Brandon. You
Yeah,
might just have
everyone
to
stop
mute
for
him
a second. James.
and send him a DM.
James.
I already did.
Arwen, can you hear me, Arwen?
Yeah, I can hear you fine.
Brandon, I'll
Can
call
everyone
in
stop
Skype
for a
now.
second, please? I'm trying to communicate with Arwen. Your microphone is super low, bro. Can you fix it?
My mic?
Yeah, you're super low. We can barely hear you.
Oh, hold on.
That's a little bit better.
Holy shit.
Let me finish what I was
guess
saying
he
there
can't
real
hear
quick.
me for some reason, Jeremy.
Yeah,
You have
ask him if
Brandon.
he can hear Brandon.
I would. Brandon, Arwen, do you have
He's on deafen.
Arwen, do you have
He went on.
Okay, let me finish what I was saying real quick. Real quick.
No,
Okay,
let
so I was asking
Jeremy
Bob
finish
earlier.
this
Hold on,
with
James.
Arwen real quick.
We got
James,
some
hold the
technical
fuck
issues.
on, dude. God
He's
damn,
trying to
okay,
help
so-
Arwen.
Hold on,
Guys,
man. He's
we have a
deafened.
technical.
I just want to finish what I said because I got to go. Okay. Anyway, so there's a 20. I told Bob if there's a 20-foot pipe, okay, and I had it filled with air and everything, and I just took a torch or whatever, like a metal pipe, and like say 10 inches wide, and I just took a pipe and just started circling around it. I just took a blowtorch and pointed at the pipe and just started walking down real slow and around the pipe and come back the other side. And then added a little moisture and all that. Okay, like the sun does. I would get gradients. I would get air currents and all that shit. That's what the sun does. The sun causes weather patterns, and there are definitely sideways gradients. There's high pressures and low pressures constantly moving around, and there's a layer like the cloud layer where, like them fluffy clouds at the top of, about a couple miles up, but the bottom of them are flat. Them fluffy clouds got so there's definitely a sideways gradient in the atmosphere, and it's always moving around. Thank you.
Not a gradient.
Yeah, I do want to address the gradient thing.
It's not. That's not happening. It's a dynamic system.
Can we, Arwen? Go ahead, Arwen. What'd you say?
Yeah, a horizontal gradient that doesn't work out, right? That only happens in centrifuges and all that kind of setup. Because in the regular stationary world, it's just one pressure difference next to another and then wind moving. That's not a constant thing. It's constantly going around. So it's not a gradient. It's just a pressure difference.
Yeah. Gradient was a bad choice of terms. I agree. But you know what I'm saying, though.
That's
Like,
what they use.
There's constant entropy and weather moving around, due to pressure differentials, due to the sun.
Right,
And
but
Arwen, that would kind of be in a
it's not part of the
static-
gradient discussion.
static environment, right? You know, what if there was if the horizontal was large enough, let's say 100 miles, and I put high pressure on one end of it, wouldn't we have? That's what wind is, right? So there's kind of a gradient, a horizontal gradient. You know what I mean?
Yeah, but it's not. But
it kind of is, Left Lane.
Well, I mean, I Googled it, and they said there's a horizontal pressure gradient force. So does anyone know anything about that? Or
Where did you find that on Google?
I Google searched horizontal pressure gradient on Earth or something. They say there's a force. Not only is it a horizontal pressure gradient, but it's a force. Coriolis is somehow
They
involved.
say hot goes to cold. They always say hot goes to cold, but
Pressure gradients can
Go
be
ahead, go ahead.
vertical or horizontal, can't they? They can be
nonsense.
It just depends on the area
maybe it's some
involved in the
Glover shit.
container.
Yeah, but the source is important because if you would have Googled that and your source was Rumpus, don't you think that's important?
Actually, there is a horizontal pressure gradient, guys. It's I don't know if it's exactly how we're picturing it or how you guys are talking about it, but it says the horizontal pressure gradient is Wikipedia.
Yeah.
The horizontal pressure gradient is a
doesn't have to be
two-dimensional vector
constant,
resulting
right?
from the projection of the pressure gradient into a local horizontal plane. Now, I don't know what the hell that means, but there is something called a horizontal pressure gradient.
I think that would be the point of the sensor. Like, so you're
Right,
wherever
so
you're taking the measurement.
spherical based geometry then, not actually horizontal.
No.
I think
It
it's
doesn't
not
have to be
even.
spherical. It's horizontal.
Hey, let's
Tell me
hear
what
from
you
Adam.
guys think
Let's hear
about
from
this.
Adam for a minute. Hold on just a minute. Adam just
Go
joined
ahead.
the show. He's not here
Just
too often.
scroll back.
Adam,
Thanks,
what's
Steve.
up, man?
You just scroll back to that definition. I think it's
Right. It's
definition
right
of
here.
Mathematics. Yeah. It's a two-dimensional vector. Yeah, resulting from the projection of the pressure gradient into a local horizontal plane. So that sounds like a mathematical description to me. It doesn't sound like a description of reality. It sounds a way of describing something. If you want to look at meteorological ways, describing and trying to comprehend how things move,
Well
you've
said.
taken your understanding of gas law and take your projection of the pressure gradient, convert it into a two-dimensional vector, so you can work with it in mathematics. I don't necessarily think that
I don't
reality.
Right.
I don't know, Adam.
It's
It
not
sounds like they're
actually
talking
a
about
literal
weather.
horizontal
I
pressure
could see that.
gradient.
Hey, Arwen, can you hear me?
Yes.
Okay. Yeah, you couldn't hear me before. That's why I'm asking.
I don't think people understood what Adam was saying, though, Brandon. I don't think they. I don't think,
Well, okay. I wanted to clarify a little bit here.
Yes, please, please, Brendan, please. Yes.
So
It does come to this next point. Yeah.
Yeah, it says its particular orientation at any one time and place depends strongly on the weather situation. So to me, this sounds like they're talking about the gradient or the difference from one pressure system to another as they push into each other.
Right. That's what I mean. It's weather. And like they say hot goes to cold, but look, like last week, front came from up north and just swept all the way down, So hot ain't always going to cold, in my opinion, on, maybe in the labs, but I don't know even about that, man. They just, I don't know. It's weather. Shit's always moving around.
Yeah.
It's the sun. The sun is what creates the pressure differentials.
Yeah, it says here wind results from my bad. Go ahead, Adam. Go ahead.
And to say what is a horizontal pressure, to me, that would sound like what I would call wind. If there's zero horizontal pressure, there's no wind blowing in my face.
Yeah.
Well, like a nor'easterly coming in.
Yeah,
it's going to have.
Curious as to the definition. If we think about gas behavior, and what does that mean? Horizontal gas doesn't.
Yeah, the gradient may be a bad explanation, Adam.
Does that make?
Yeah, it is
I'm
an
just
gradient.
wondering what it's claiming in reality. what a horizontal pressure gradient is my point.
Yeah. Unfortunately, there's no more details in here, but
what I was referring to is like cold fronts sweeping across the lands,
Right,
like
Brian,
cold fronts and warm fronts.
let's just say a hurricane could be a local horizontal pressure gradient where low pressure down low getting sucked up, causing the spinning. A tornado is another one, right? But they're not. Yeah, they're not wide scale across the whole country or a whole area. Those are very local. Of a, I'm getting at, right? The idea of pressure going from one to another very quickly and causes that spin. Which is wind in a static environment or in, generally normal environment. It's called normal, where the sun's out, everything's doing good. You'll get gusts of wind. Okay, cool. Not a tornado.
I think Jimbo's right too. It has to do with the moisture, because even when it's windy, you see the cumulus clouds, like I was saying, you still see a flat bottom of them clouds with the wind moving.
Is huge.
And the clouds are moving left to right, but the wind, it's still flat there at the bottom of that cloud layer.
Yeah, exactly.
So I'm getting confused on the logical meaning of pressure. In gas pressure, that requires a container. Any other pressure requires two surface areas. Am I correct?
Yeah. They're talking about the winds would be supersonic speeds rushing up, and I tell them that if it was an infinite vacuum up above us, that's when the winds would be rushing in supersonic speed. They're thinking backwards, bro. So they got you confused.
Well, when you're walking into wind, it's harder to walk into it because of your surface area and the tiny particles hitting you at the opposite speed.
Right.
Opposite direction at a high speed.
Or let's not call it tiny particles.
So no matter what, pressure requires surface area.
Tiny particles
yeah.
Or not, but
just no matter what, any kind of pressure.
Walking through a pool of water, right?
Brandon, can I ask a question on that? Just again, for understanding, I think when we talk about pressure gradient as we understand it from low to high altitude, it's defined. I can comprehend it. I'm struggling to comprehend what a pressure gradient is in the horizontal, and certainly there appears to be no direction of this pressure gradient. Is this a randomness that it can be expressed from left to right, right to left?
How about a valley?
Is it always expressed from one direction to the other? It doesn't seem clear what this.
It's patterns, Adam.
Well, the thing is when we get to hold on, Brian. The thing is when you get to
so
when you get to Alaska, you have a higher pressure, right, Brandon? Because of it's so cold. I mean,
the North Pole. They said at the poles the pressure is higher.
Yeah. So as you go north, you would get a higher. It gets colder and colder. You're going to get a higher pressure from the temperature.
Yep, and then if you go towards the equator, you're going to get a lower and lower pressure on average. But yeah, I see where you're struggling with it, because it is kind of random because of the weather system. It's not like an even
it's dynamic
gradient from North Pole to equator, South Pole, from the south to the equator.
Those pressures.
But then again, in altitude, is it an even gradient always? I mean, that's dependent upon the pressure, updrafts, downdrafts, weather.
Yeah,
movement.
exactly. Hey, that's it. Hey, Brandon, when you were talking about the air rushing up there, it gets caught up in them jet streams, dude. It just starts hauling ass all over the place. It's patterns, it's streams, it's just weather, man. But yeah, maybe gradient might have been a bad term for me to use, for lack of better words, Adam. But yeah, it's entropy. It's weather, entropy, whatever you want to call it.
It seems to be a result of a dynamic system, from what I'm seeing. So what they're doing is they're taking a three-dimensional world
and terrain
with all of that dynamic system, expressing the 2D plane, and then quantifying all the different pressures you get across that 2D plane, and saying that the variance across these is that. Well, that's just exactly as you say. It's an expression of the dynamics of the system and entropy. That if I blow, then there's going to be more pressure at the point where I started blowing, and behind it will be a lower pressure system. That's kind of what it seems to be describing, that these things are then measured. It doesn't, to me, equate to the up-down pressure gradient, which has a different nature in of itself that we've yet to define.
Yeah, I agree with you on that. That's well stated. Yeah.
What causes waves to form on a lake or on the ocean, right? What causes those waves?
Wind.
And that would be a pressure change horizontally, right? If the pressure was straight down, it would just be, the water would be perfectly flat. It'd just be high pressure straight down. But what causes that horizontal undulation in the water is a horizontal pressure change.
Right. It seems like the waves are always moving toward the land, it seems like.
Oh, yeah.
Well, when I was saying earlier, when you, like the density tower with liquids, you can do that with gas. You just got to color them.
Yeah, but think about what Brian.
So hold on. The vertical. What I'm saying is the vertical, right? Is the layers, and the horizontal is also the layers.
Yeah,
so you have a difference in pressure horizontally and vertically.
Yeah, think about what Brian just said, right? Brian just said that all of the waves seem to go toward the shore, right?
Yeah.
Okay,
just going to say this, Travis.
Okay, hold on. Think about it. If it's a lake, there's a shore in every direction.
Exactly.
Dude, ocean waves, they go to the shore, and then when they hit, they go under, and then at the bottom,
No,
it
you're
goes
missing
in the
the
other
point.
direction.
You're missing the point. You're missing the point. The point is, I've often thought about this too. When I'm shooting out at the Channel Islands, I'm looking at the waves coming straight at me from the islands, but then when I shoot in any other direction, they're moving in other directions, right? Yeah. And
but here on the East Coast, sorry.
Now I'm just saying that's just always blew my mind. But anyway, going back to what Brian said, and what Aaron is talking about with air or wind going across the surface of the water is more viscous, is that the word for it?
Sure.
It can be moved
surface
easily
area.
it can be moved easily by such a light pressure. But the point is that the waves go in every direction to the shore. It doesn't just go to the east shore.
It can't be
the
just
waves
wind
tell
that
you
causes
the
the waves
surface
to
area of the
It can't
water.
be just wind. Okay, and this is why.
Well,
because
hold on a second.
When
You made a great
even when
point.
there's a west wind in Florida, it just holds the waves up coming to shore a little bit longer. There's never any waves starting here at the shore working their way out 10 miles. If you get out there far enough, then maybe. But so it's got to have a little bit of something to do with pressure and wind.
Sure.
Well, you don't have just one huge wave, right?
Vector, exactly. It's dynamic, everything.
Hold on, guys. You don't have just one huge wave, because he made a good point just a second ago. The wind on the water hits a surface area, and it only moves that surface area proportionate to its strength or speed, direction.
Yeah.
It doesn't just create one huge wave.
Right,
because it creates multiple waves.
Yeah.
And it does it on a very on a particular surface area. It'll grab so much here, make a wave. So much here, make a wave. It's the surface area.
But it
that's
pushes
being
the whole
affected
body of water,
and
and then
ignored.
it splits up. Basically, the bottom of the ocean is moving in the other directions as the waves are top. Otherwise, the water would be heaping up on shore, and that doesn't happen.
I wouldn't say that it's moving in the opposite direction, though, Arwen. I would say that it's
Yeah, it is.
Okay, hold on.
The water's not heaping onto the shore.
Okay, just a second, Arwen. Okay, I'm saying that in the same way that when we're above the surface of the water and the wind seems to be all around us, but we feel it blowing, but it's not like I can say like it's just coming from this one direction entirely. It's like dynamic around me. You go down under the water's the same way. It's just dynamically moving. It's not, I don't want to say that there aren't currents. That's not what I'm saying. But I'm just saying that it's not a universal every single time. It's the same in every location. That's what I was trying to.
Yeah, it is.
No,
Otherwise,
it's not.
there would be all
No,
kinds
it's
of weird
not.
dynamics going on. For every water being blown towards the shore on the surface, the water underneath has to move in exactly the opposite direction. Otherwise, there would be
How far
a giant
down?
mass
How far down,
displacement.
Arwen?
Turbulence doesn't allow that.
How far down, Arwen? Locally?
Yes, he's correct, man. When you have a fucking sinkhole, right? You get
Who's
water
correct?
displacement.
James, who's correct?
Arwen.
Okay.
In a sense, not entirely.
No, Travis is right. It ain't always. It's most of the time they're at the shore.
In a
The waves
sense,
wash
not
by the beach and then
entirely.
come
You got
back
Brian
out.
for
But
Travis.
not
you got
always.
James for Arwen. Anybody else?
Well, for every body of water at every part that moves in one direction, underneath it,
How
it has to
far
move the other
down?
direction. Otherwise, the entire mass of it would displace and start
How
leaking
Only
out.
the
far
surface changes
down?
shape in equilibrium, Arwen,
How
right?
far down,
Yes, the
Arwen?
surface
Wave
moves
form.
towards the one direction, and underneath it goes in the other direction. You don't
How
see
fucking
that.
far down, Arwen?
Depends on how deep it is, Travis.
That's
It's all
that is a
relative to
non-answer.
the experiment.
Okay, so no,
It's
stop,
all
James.
relative.
Stop, please, stop. So Howard, all the way down then?
Yeah, you know when waves are coming in on the ocean and it's dangerous because of tides and undertow, that's water going back out underneath.
Okay, stop.
Water
Howard,
finds its level.
Howard,
We're in the
Part of it is
center of
going
the
to be
ocean,
blown on the
Left Lane.
you
shore.
say
Go
the
to the center.
stupidest things sometimes, man.
Yeah, you've never heard of riptides and undertow?
I didn't say that. Are there riptides and undertow every single day at the beach?
Not
When
not
there's
necessarily.
waves.
No,
Yeah.
fuck
Yeah, it
no. Then
depends on
your answer is irrelevant.
Riptides and
Whatever.
undertows are definitely correlative to the wave height size.
And we're not
the
talking
crest,
about
the
that. We're
crest.
talking about being out on the water, okay?
Yeah.
We're not
If
talking
that
about
obviously
the
the
water
direction,
coming to the
there's
shore.
going to be a stream the other direction underneath it every single
Howard,
time.
are there
How far
riptides?
down, Arwen?
Howard, are there
obviously
riptides in
the-
the center of the
underneath it.
Pacific Ocean? Are there riptides and
Obviously, the
undertows?
water
No
has to
matter
go
where
back.
the drain hole is, guys,
No,
no
man.
matter where the drain hole is, as soon as you pull
Obviously,
the
the water
plug,
has to.
all the water
Obviously,
starts
the
to move. All of it.
Right.
Obviously,
But the wave coming toward the shore, there's a peak and a trough. It's not like it's going back and forth. It's coming. The wave is coming. The wave is rolling toward the beach because behind the wave is low. And the whole body of water ain't moving toward the damn beach. That's not right.
It's
Well,
on
it
the
just
surface,
depends
it's
on how
kind of
much
being
wind
pushed
there is. You
forward
can
in
see
that
on
Listen,
direction.
we're not
And then
talking.
it
various
moves
cities.
back.
We're not talking about the. I mean, I guess to a certain extent, Brian talked about the waves hitting the shoreline. Okay.
The shoreline.
Yeah, the shore, right?
The
So
resistance.
I
shoreline.
get the physical dynamic of the wave hitting the shoreline because it's running into something that it can't move, and then it's got to have that equal and opposite reaction, whatever you want to call that.
Seeking equilibrium back to flat.
Okay, but
Yeah.
when we're
He's got
talking
a
about,
point, man.
let's say though that we're out on a lake and it's absolutely no wind, right? No wind, no ripples or anything like that, and then the wind picks up, just like if you were to in a sink blow across the water, right? Your breath is going to send a reaction in every direction. It's going to be stronger in the direction with your breath, but the equal and opposite reaction in all of the other directions is going to have still ripples going out in those opposite directions, right?
Well, you'll have. See, where I think Arwen's right
You have a
is
single pressure source
Okay, just
causing
go
all
on
that.
what I
Yeah.
just said. Don't go away to something else. I just asked a question. Am I right?
Yes.
well. Let me try to clarify. Right?
No, you
If
either
you
say
drain
yes,
a
you're
if you
correct,
drain
or
a
no, you're
bathtub,
incorrect.
if you drain a
Are you trying to
bathtub,
clarify my question?
Or come up
yes,
with a new analogy.
yes, if you let me.
I'm trying to understand what you're saying, James.
When you
because
drain the
I asked
bathtub,
question.
Why do little waves crash on all shores of around?
Can I help here or not? Can I just finish my point and then you'll see if it's
Go ahead. I
clear?
hope you actually do it. I hope you do it. Go ahead.
Okay. If I drain the bathtub, right, the water directly above the drain is not the only water that goes down. Now, for all the water to go down level requires it to be moving in all directions.
Yeah, I don't think
Okay.
that helped.
Man, that was great. That
The
was
wind
great.
does this. The wind does the
I don't
same
think.
thing.
Can we have a?
If you move the top,
Can we have a
if you
vote on
move the
that one?
1 inch surface of water on the top,
Can
you're
we have a
moving
vote
the
on that
other
one?
water under it in the other direction.
We're talking about
Okay, hold on.
horizontal
No. So
we're talking about.
can we have a vote? Did James clarify my question?
No.
No. No. Anybody else?
Not even close. I don't even know. And I'm just picturing
No,
Travis
he didn't,
in the
man. He
bathtub
didn't.
now.
He did make a point, but it wasn't.
You're saying
wasn't
that.
clarified.
James,
Okay, maybe I
That's
misunderstood
why I
Arwen.
stopped you, James, because you don't make.
Well, I
sense
might have
sometimes, bro.
misunderstood Arwen. I thought Arwen was saying that, in water,
Arwen thinks
water
waves is
moving in one
water
direction.
moving. Arwen acted like the water is moving
Bro,
from the ocean
why?
toward the shore. That's not
So
what
I
waves are.
can't even
Waves are peaks and
clarify
troughs.
that.
Why would you address?
Like, let me
Why would
just
you address? So hold on, James. I asked a question, and then I made a statement, and then I asked for the panel to evaluate my question, and then you jump
Based
in
off
and say,
Arwen's.
"Oh, hold on," and then you jump in and say, "Hey, I got a clarifying question point," and you go to Arwen. Why are you going to Arwen
In bathtubs.
when I'm the one that made a point and then asked a question? Why?
I thought it was Arwen that brought up the fact that water moving
I was
in
the
one
one who was
direction
just
requires
speaking.
it to be moving in the other.
It was actually
that's
Jeremy
where
who
I
brought
went
up
wrong.
the original question about horizontal pressure gradients, and that's what we're kind of trying to get at. And I brought up the idea of water, what causes water to undulate. It's got to be something horizontal. If it was a vertical pressure gradient, you would just have a big dip in water. Yeah, there might be waves going on.
Like I said, with the
side,
drain.
but,
That's what I'm getting at. I was on point.
Not
So when you move water one direction, if it's the wind creating the waves, you're looking at the water, it's moving to your right on the surface. When the water moves on the surface to your right, the water under it is moving to your left.
That's bullshit, dude.
Because it's going down level.
It's peaks and troughs.
It's going down level.
Prove that.
It's not just going down right there.
How could
Yeah,
you
it does.
even
That's why
prove
waves
that?
go back and forth when it comes.
We're talking
returns,
about
it
a
moves
propeller.
underneath
on
the
the
waves
water,
that are
propeller.
not
coming.
the shore.
That's exactly
That's what a
it does.
propeller does.
If it was all
Air
the
and
water moving
water.
with the wave, it'd be a tsunami every time 1 foot waves came in. A tsunami's only like 2 or 3 foot high of water, guys.
I don't
Have
know
you
what
ever
the
And
fuck
we're
you
talking
guys are
about a large
talking about.
area.
where the waves fall? Right?
I
If
apologize
you
if I
form a
was off
ball,
Bro, I
you're going to
surfed
be
my whole
rolling,
life, man.
rolling back and forth. Because
Right. It's
on the
peaks and
top
troughs,
side,
bro.
you're going to be pushed towards the shore. On the
It's
bottom
peaks and
side, you're going
troughs,
to
bro,
be
and they do break on the
pulled
shore
back
and they do
into the
roll up on
ocean.
the beach.
Brian,
And
Brian,
then they
let
come
him
back
finish,
out.
bud. Brian,
My
Brian,
bad,
let him
my bad.
finish. Go ahead, Arwen.
Go. Oh yeah. Jeez.
Sorry.
Right. So if you're going to form a ball in the burning, right, at the beach, you're going to sit. I used to do this as a kid. You get all sanded up and all that shit. But you just start rolling because the top of the wave is going to push you towards shore. While as it retracts, you're going to be pulled back into the ocean at the bottom. So you're going to keep on rolling because it's a constant stream. The waves come
Only
on
to the
shore,
extent of the
then go
trough.
flat.
Only
Can I
to the
finish?
extent of the
Then they
trough.
pull back underneath the new waves coming.
You're
And
not
they
to the
goes
bottom
back,
of the
and it
ocean,
keeps going
Arwen.
back for a while,
You're
for
not
a
being pulled
distance.
to the
When
bottom
you
of the
throw a
ocean.
rock at a 45
Holy
degree
shit.
angle
Damn,
in
guys.
a pond, the ripple goes all the way across. No matter the angle you throw it, the velocity, the water travels in a circle from the contact all the way
so it's
through
not
the
pulling
pond.
back out in every direction. It's
So
pulling
it's
out
going
in
in
it. It's a
all
peak and a trough,
directions,
guys.
not just the opposite.
What does this have anything
All
to
right,
do with? By the way, I have no idea why we're talking about waves.
Yeah, I don't know. We went off on a tangent.
Lateral movement, horizontal
Talking about
movement.
air
When it
pressure
hits
and
the shore,
horizontal.
it goes sideways, and this is ridiculous. Where's it going to move to? The other wave right next to it? No, it's going to go the only way it can go, straight back underneath it. Not going to go sideways. There's no maneuvering room.
Just reading something here that
A
says
wave.
waves transmit energy, not water.
Exactly. That's what I'm trying to say, but I couldn't word it so precise. It's not a wave just rolling up on the beach. It's peaks and troughs. But it does bounce up the beach and roll back a little bit, and there is rip tides, but not always. That's what Travis said to begin with. It's not always are there rip tides and undertows.
Well, you can't have the water just.
Yeah, there is.
You can't have the water just going in one direction constantly. Otherwise, all the water would be on the land.
Right.
So Jeremy,
So
I
was saying
actually,
it goes in all directions. Going to be equal and opposite as strong as the big waves coming towards the shore. Equal and opposite strength.
I'm actually on a podcast with some fish, and some fish actually told me that there's nothing happening down there. Right? They're just chilling. Everything's fine. You know.
Chilling like a villain.
They're not wondering what wind is and wave undulations on the surface. You know, fish got it figured out. Apparently,
they're not wondering how you can have gas pressure without a container or nothing.
Yeah. Well, they got brains.
Well, they would be saying water pressure, but same thing.
Yeah.
But this says waves are most commonly caused by wind. Wind-driven waves or surface waves are created by the friction between wind and surface water.
Yep.
And it also says that waves are created by energy passing through the water, causing it to move in a circular motion. However, water does not actually travel in waves.
Friction, which could also be called pressure, right, Brandon? You know, wind friction on the surface of water. You could call that pressure because as a wave forms, there's going to be a resistance. Okay, you're going to have some pressure there. And then, like Arwen says and everybody else, temperature. Boom.
Yeah, that was what I was going to say, man. I've been surfing my whole life, and right before the wave, the water kind of pulls you back. That's right when it hits the beach. It's not really doing that until right when it's rising up, about to curl and break. The water pulls you toward the wave. It's just the water going up and down, peaks and troughs, man.
I can picture Brian surfing, being a surfer dude.
I cannot. Brandon, I don't like to be critical.
Gold chain, spike hair, hell yeah.
Go ahead, Adam.
Within your source, at the bottom there, it does say, I quote, the gravitational pull of the sun and moon on the earth also.
Oh, God.
I'd be a bit dubious on these guys.
How did we go from the bottom of the ocean now to
moon?
Yeah, this isn't the greatest source in the world. But this is confusing me why they're saying this, that waves are created by energy passing through water. The water doesn't move because we do know that there's such thing as undertows and underwater rivers and all that shit. So I don't know.
Yeah. Underwater mountains and.
If it was the sun and the moon controlling the tides, wouldn't you expect the biggest deviation of tides to be at the equator? You know, in between the tropics, since that's where the sun and the moon travel from. If it's pulling all the water on Earth towards those spots and then away from those, and then away from those spots when they're.
Yeah,
my bad.
Dude, they don't even know how to calculate this supposed moon pool.
Those are the weakest points of tides, right, Jeremy and Arwen? Right, those are the weakest points of tides.
Yeah, that's where you get the least. You get the least deviation in between the tropics usually.
Because we already have.
And you get the
bulge,
highest.
Jeremy. We already have the bulge. That's why.
The bulge.
They dodge that topic like the plague, guys. You start bringing up tidal nodes and how there's spots on the beach with no tides at all, and they just dodge it like the plague.
There's places where there's tides 3 times.
Nads and bulges.
Did you know that?
No, I did not.
Sorry, what'd you say, Arwen?
There's places where there's 3 tides. Tides are like really weird things.
Agreed.
Yeah, they're obviously.
And when you got the sun and if you got the sun and the moon,
high and low, sometimes multiple times.
if the sun and the moon are in the sky close together, why aren't the 2 high tides of the day only 2 hours apart or an hour apart?
Yeah, one of them eclipses, right, Effie? One of them eclipses. There should just be massive tides.
Oh yeah, when you have a solar eclipse, you should have an insane tide, a high tide on that side, and then a very low tide on the other side, like drastically.
Yeah. Only one high tide that day. That's it.
Wouldn't you also become drastically lighter? Like, wouldn't you weigh less under the moon
I'm telling you guys, buy gold
drastically.
when there's a high.
I
Buy
wouldn't
gold
build a
when there's a
house
soul.
on
Listen,
the coastline on a ball.
If the moon
financial
is picking
advice,
up
but
all that water,
buy gold.
wouldn't you weigh less under it?
Yeah.
What'd you say, Jeremy?
I'm just telling you guys, this is not financial advice, but the time to buy gold is when there's a solar eclipse right above you, and then you want to sell it when there's a solar eclipse antipodal.
Yeah. A lunar eclipse.
That's how I've made
Okay,
my
just real
fortune.
quick.
Solar.
Isn't that like a
Jeremy
huge
is
proof that
incorrect when
everybody
he
just
was
looks
talking
over or
about
not?
the
I don't know. My wife always weighs herself on a full moon. That lowest value
Well,
ever.
hold on, guys. Isn't that
My
like
wife
a
doesn't.
huge
That's when
proof?
she turns into a werewolf, so
I
she
mean,
doesn't weigh
just
herself on the
a
full moon.
comment on to me, this is one of the weakest play and a great point to start conversation with normies on. You don't even have to get into the nature of Earth on it to show that within their model, the tides and the moon don't match. You know, it's one of the weakest points they've got because they don't even have correlation. It's fundamentally, even on this one, if you get my point,
right. But let me
real
tell
match.
There's only one correlation here where I live, and that is they fall back behind about an hour a day. That's the only correlation. But yeah, that's period. That's place dependent.
It correlates to
Jeremy,
not consistently
but
not correlate.
real quick
Yeah.
on Jeremy.
There are two tides a day, right, Brian? I
What
don't
the
live
fuck?
on
Can
the
you
shore.
guys not hear me talk?
Your mic is
Sorry,
a little bit low, but we can hear you.
Travis, you're lower than normal. Just so you know.
Why?
Aaron doesn't give a fuck anyways, but
I haven't done
I'll
anything
overtalk
different.
everybody.
Yeah.
Have I been low? Have I been low this whole time?
Yeah,
No, you're all right.
All right.
We
Well,
can
you were
hear
high
you.
on Friday, now you're low today, so it kind of balances out.
I just wanted to touch base real quick on what Jeremy said about the tide shift.
That was funny, Effie.
There you go, Effie.
What the fuck?
Thanks, guys. I thought it was pretty good, but anyway.
I just got it. That was great.
Go ahead, Travis.
So the moon
Go ahead, Travis.
allegedly.
Travis.
Jeez, James got a
Travis.
point.
Travis, go ahead. Did he hear? Or?
Go ahead,
Travis, you didn't hear what Effie said. It was a great joke. He said you were high on Friday, but you're a little bit low today.
That was a good one, but he's trying to say something, and we're not letting him.
All right. Has I dropped and came back? Is that any better?
You're good.
Much better.
You're good.
Much better.
All right. So I dropped and came back. Okay. So look. So Jeremy said what I think most people think, because I've asked a couple people this, but I think it's backwards. Okay. I've been shooting at the Channel Islands, and the moon is nearly full in the daytime, right above the Pacific Ocean. Okay. If the moon's mass is drawing the water to it, I shouldn't have high tide.
Exactly.
But I did. It was all the way up to the fucking rocks. I couldn't even get to the beach. And I'm looking at the moon going, wait a minute. If the moon is the gravity of the moon is putting the water, why do I have a high tide? It doesn't.
Well, if the moon's right above you, and there's a high tide in your area, that would fall in with the globe.
No, it's
That actually
backwards,
makes
bro.
more
That doesn't
sense
make
than
any
my
sense.
argument.
That makes no sense.
Yeah, that
The globe. Hold on,
that makes
James.
more sense than my argument,
model,
Travis.
hold on, James. In the globe model, they're saying that the moon is pulling the water, and therefore, when
it's
the moon's
away
above
from
you,
me,
you should have
Jeremy.
high
No,
tide.
it's over the Pacific. It's not above my head. It's over the Pacific.
That it was above you.
Yeah, it should be pulling the water away from him, and even when it got over your head, it should pull the land up as well. By their claims,
the land
you would weigh on the scale much lighter
And the
on their
light
claim.
should pull the light.
But
up,
what
too.
Travis is saying makes more sense than my argument. My argument is if it's picking up all that water, when you're under it, you would be lighter. His argument is, which makes more sense, if it's picking up all that water, it's taking the shore water to it.
Right.
It's not bringing water to the
Rivers
point.
flow faster and shit, right?
and their Lagrange points out there in space should be tidal.
Guys, we got Arwen and Adam Meek in here. We got Arwen and Adam Meek in here. Let's at least
point. Sorry.
Adam Meek in here. Let's at least try to sound like we know what we're talking about.
Oh, it's way too late for that, Jeremy.
No wonder.
I like that thought there, Travis. That's awesome.
Well,
Yeah, it should be pulling it to the moon.
I brought it up
Pulling
quite
it
a number
away
of
from the
times.
shore.
New show name, Brandon. It's called Monday Funnies. Right? Monday Funnies. We just act like we know what we're talking about on
Monday Fun Day.
Yeah.
I got just another point. Like, if the moon is lifting all this water up, either towards away or towards itself, then that's a hell of a lot of weight that it's lifting, effectively lifting it from the Earth, the weight of it for a period of time, and then putting it back down, lifting it up, putting it back down. How does the Earth maintain this perfectly steady rotation and forward momentum if it's got billions or trillions of tons of water going up and down on its surface?
Wouldn't it make
Sounds
more
like
sense?
a lot of
Effie?
drag.
Wouldn't it
You'd
make
have
more
a
sense?
lot of drag off of that. Huh?
Can I
wouldn't it make
top
more
that
sense?
question? Can I top?
Effie,
Not
Effie,
only that,
wouldn't it
but
make
you're
more
adding
sense?
Why
weight
don't
to
the
places like
clouds
New
move
York,
up towards
Effie,
the
Hong
moon?
Go
Kong.
ahead.
Effie, wouldn't it make more sense instead?
Go ahead, Erwin.
I was just saying, like, if supposedly the oceans would move towards the moon, why don't the clouds do the same thing?
No shit.
Right. Cloud type.
Making any sense.
Yeah.
Tides and clouds. I've actually asked that before. Yeah.
I think what they say with the
It should
moon is,
happen.
though, this is how I
Layers of
understand it. So
bullshit
you've got the moon
being
going
uncovered.
around the Earth, right? In their model. And if it's on one side, it's pulling all the water to that side of the globe, and the other side of the opposite, the moon is experiencing low tide, and then vice versa. It's experiencing high tide.
Which is stupid if you think about it,
Yeah.
because I wish I had computer graphics. Think about it, Brandon. If the moon, like if the full moon was out over the Pacific where Travis is at, but there was a high tide where he's at, so that's showing the water higher where he's at, and the moon pulling up higher, way the hell out off in the distance too. So
Right.
it doesn't make sense. It would have to follow the moon around. The bulge would have to follow the moon, and it does not. Adam was right.
Well,
to
no, if you
begin
could
with.
see,
The thing is,
if you could
if
see
this-
the moon, you'd still be on the side of the Earth where the moon would be impacting, right? Because 12, if you still see it, that means it's probably about 6 hours away from you, or so, right? And then after that, after it goes beyond the horizon, it's on the other side. Then you should be experiencing a low tide at then. But if you see the moon in the sky, it should be on your side, right?
Yeah, the way they describe
the thing
it,
is, if the moon was actually doing this to water on Earth, you'd be able to see it in a cup of water. It'd move the water in the cup.
It's not massive enough. It's not massive enough.
So gravity is specific to.
Yeah. It's
You don't
very
understand. You don't
very
understand.
tricksy. I did a debunk on this. I've got 3 debunks on this, and that's the one thing I talked about with gravity being very tricksy. Yeah.
Huh. Well, my question is, what is the
See,
official
I've always
explanation
thought
for
of,
these nodes on the Earth, these tidal nodes? What's the official explanation?
Amphoric. What's the other name for them? Amphoric? No, I can never pronounce that word. Amphoric or
The tidal
something?
waves is the moon.
Does anybody know what the official explanation is?
I've never looked into them, but they're absolutely
For
amazing.
tidal waves?
No, for
Brandon,
nodes.
for tidal waves?
For nodes.
The nodes.
Oh, for nodes. I'm sorry.
No,
They're called like
Yeah.
amphoric nodes. Or
I
something.
heard someone talk about it once and said that it had to do with maybe the Earth's filtration.
That's what I think. That might have been me, Travis, because that's
I think it might have been you. It sounded really smart.
It definitely didn't come from a
See,
glober.
I've always thought of, even at the 7th grade, because I asked my science teacher this, I've always thought of the Earth in space. This is back when I believed it was a ball, as a balanced wheel, meaning its shape right now, whether it's a perfect sphere, oblate, spheroid.
Yeah.
Once we start
There's an axis.
taking, once we start taking weight from one area, places like New York, Hong Kong, we start taking weight from one area, moving it to another. Wouldn't you affect the balance, the spin?
Depends
Like
on
how-
what the
how could
depends on
Jack,
what the
that was what
ratio
point
is
formed
between
the
all
Earth.
of that matter compared to the overall. But yeah, I would think that this sphere that's perfectly rotating and flying through endless nothingness at a constant rate would need to be pretty well balanced. But I'm sure they could come up with some plausible mathematical
Brandon, on with regards to that, then, because obviously you take into account we've got this large moving mass of water, then the only way in which tides could account for that would be for them to follow. Wouldn't it be the celestial movement of the supposed thing that's the causation of the tide? So they would have to be completely in sync, and so in sync that over the billions of years that this has occurred, that it doesn't affect any other part of rotation or wobble or anything else, because that's the only way in which it could happen without it being obvious.
Yeah, I agree.
That reminds me of them talking about the velocity of the Earth, and it's spinning. They say it's so big and it's going so slow, but when I talked to them about it, I said if the Earth were to slam on brakes, what would happen? And they say that everything would fly off at 1,000 miles at the equator. If the Earth slammed on brakes, then everything would fly off, including the air. Even I think Essie, or not Essie, but what happened to Khalik or whatever his name was? He disappeared, but he said that even the air would fly off at 1,000 miles an hour. So that's how I look at the velocity. If something slams on brakes and flies off that fast, then if you're going to scale it, you got to think in terms of just that, of getting something to move at that speed. But they don't look at it like that.
I thought the air was in lockstep with it. So if irrespective of, because remember we've got it going, spinning at 1,000, orbiting at this, celestial orbits, galactic orbits, doing all those things, and that atmosphere stays in lockstep. So if it did go on its brakes, surely in Narnia the atmosphere would stay the same, because every other bit of inertia doesn't affect it.
Yeah, but if so the air would slam on brakes too. In other words,
well, it's in lockstep.
Yeah,
that's their definition. Lockstep.
Listen to this. Sorry, I was half paying attention. I don't want to divert away from what you guys were talking about.
I was only being flippant anyway, because it's nonsense. If the Earth stopped spinning and hurtling round this thing, and we had brakes, that's how you prove a ball, is it?
Yeah, there we go. That's what we.
The other thing, just quickly, Adam.
There's our experiment.
The other thing, Adam, is when you're talking about the ocean being in perfect sync with the celestial objects and all of that doesn't make sense, because the ocean is so dynamic that it couldn't maintain that perfect synchronicity for that amount of time. I mean, just go back to 2004 with that massive worldwide tsunami. You got an enormous amount of water traveling in multiple directions all at the same time, hitting different coastlines at different times. That would throw that perfect, balance and synchronicity out of place. And there's plenty of other tsunamis. So, that fanciful story of that's how it works, I don't think does actually work.
No, I'm not saying I wasn't postulating that as a.
No, I know, man. I'm just saying I understand just the tongue in cheek. I understand.
I was aware of these things called continents in the way of this possible rotation to keep it in lockstep that would interfere, and that's the farce of it, isn't it? Like I said at the beginning, it's one of their weakest points, because outside of that postulation that's doing it, they don't even have correlation of the position of the moon to the tides, really. So,
right. And this is what they're saying. Listen to this from the Ocean Service NOAA. Listen to this paragraph I just read. Tides originate in the ocean and progress towards the coastlines, where they appear as the regular rise and fall of the sea surface. Thank you. Since Sir Isaac Newton's 1687 discovery, we know that tides are very long period waves that move through the ocean in response to forces exerted by the moon and sun. However, and they have this in italics, these gravitational forces do not control when high or low tide events occur. Other forces more regional than the moon or sun control the tides. Talk about some fucking double speak, right?
Yeah, that's great.
What?
That is absolute gold right there. Wow.
It's because of the moon and the sun, but they're not actually anything to do with it.
Right, and then it says many of them have to do with the geography and shape of
Why are
the
you
Earth.
talking about the flat Earth right now? I thought you were talking about the globe Earth.
Huh?
You're describing everything. That's the great scale negator, right? Everything we see from our perspective is because the Earth is an extended plane in front of us. So all of our observations are going to be exactly the same. So the way that we describe them locally, that's just what they said. They just gave credence to a local flat Earth model, even though they have a pseudo-scientific globe model that's up at a higher level that they say is really happening.
And that's how Rumpus.
Yeah, I like that. Well
And
said.
And that's how the Rumpus. Hold on, and that's how the Rumpus was describing the horizontal pressure
gas
gradient
pressure.
locally.
Yep.
Yeah, they just describe it on a local level. Exactly.
Hold on, Travis. And I wanted to address James and Jeremy about when we're talking about gas pressure and atmospheric pressure, and Brandon also. Remember, Rumpus only thinks in one little one cylinder, 25 miles high. That he can only think of that one point, and he can calculate every single fucking, level up to that, that cylinder, because I think it was James that said grab a 20-foot, 20-mile pipe and put it up. Well, yeah, Rumpus can do that, but remember, take away the pipe, and Rumpus can't calculate that. Right. That's why we had the argument of the dynamic system and everything. And
he thinks Earth's atmosphere has a volume. Yo, newsflash: the volume on your Earth's atmosphere. Hold on a second. The volume on Earth's atmosphere is the fucking universe. That shit never ends. Remember, it keeps going and going into a gradient, smaller and smaller. There is no fucking volume. It's the whole universe. Is your volume for gas pressure?
That's why I say don't give him the volume. Don't give him that pipe, because that's kind of a how to say this, illustrative point of view. Like, okay, here's a pipe. If I heat the bottom, I heat the top. Brandon was talking about it with Rumpus for a long time. They can calculate every single point on a pipe, right? But when you take away the pipe, they have nothing. But as long as you keep that pipe, and that's when Travis came in and was like, dude, you guys got to stop arguing with these motherfuckers about this shit, right? Is because as long as you keep that pipe, they can calculate shit mathematically. It may be true or not, who knows? We don't know. Nobody knows. But if you give them a reference point and something that's contained, oh, fuck, they'll calculate shit out of that. But take away the pipe. And that's why they always bring up the pipe. If you take a pipe, blah, blah, blah.
Well, you can have an open-ended container and you can have a double open-ended container, right? All measurements will be done.
Rumpus was talking about Brandon from Mount Everest down to the ground, right? But somebody brought up the idea of a pipe, and that's where Rumpus was arguing with Brandon. Because, yeah, Rumpus can calculate that shit all day long. No big deal. But take away the.
I wish when Brandon was arguing with Rumpus, you guys would have gave him a couple of minutes, at least a little quick.
But take away the pipe. Brandon was with no pipe. I remember that. But people were chiming in, going, "What about this? You put."
So this is going to sound silly. I'm sorry. When the judge sentences somebody to life in prison, was that based off mathematics?
Pretty much profit, loss, calculations of debits, credits, social,
it was based off evidence.
Scores.
It was based off evidence, and sometimes you're sent to prison innocent.
It's based off math.
Sometimes you're guilty and you get away.
How much can we get from you? Whether you're time labor.
Yeah, so the only math that is generated in the judge's calculation on whether to let you go or not is the math that tells him how much he's being paid.
All right. On that note, we'll end the show for today. It's 8:00. Hope everybody enjoyed the show. Kind of a strange conversation, weird dynamics on the show tonight. But it's all good. I never know what to expect. We will see you tomorrow at 8 o'clock. 5:05 Eastern Standard Time, normal time. Not sure what's going to be going on tomorrow, but we'll figure it out, and should be fun. So thanks everybody for stopping in, listening to the show. Appreciate it. And hit the thumbs up on your way out. That's appreciated. And we will see you tomorrow. Bye, guys.